morning, everyone. Okay, so welcome to IPU. Thanks a lot for accepting our invitation and for coming all the way to the AI for Good. And today, I'm privileged to be one of your hosts for the tinyML workshop. And I hope that we are going to have nice connections, nice discussions, interesting presentations. So I just want to go through a quick couple of housekeeping things that we have here. So if you need any assistance, you can find our friends who are in a t-shirt called "How May I Help You?" So please don't hesitate to ask them for something that you need. And of course, I think this is not interesting for this group, not this one. But if you need to see what is happening in the program, you can download the app and then you see all the program and the live sessions as well. We also have Wi-Fi, so on your badge, you have the login and password. And if you have a leader's pass or a VIP badge, you can access the VIP lounge. Coffee is available throughout the day. Lunch will be available there as well. And also you can access the networking session activity that we have in the evening at WTO. You can come for the reception and network with others. So yeah, I think with this, if you have any questions, please don't hesitate to ask us for help. And thank you so much. Enjoy the session.
Right, so let's get started. So as I hope you know, you're here for the tinyML session. Please leave now. We won't hold it against you. So at the beginning, what we're going to do is Didem and myself are going to start with a 15-minute chat each just to set up and talk a little bit about tinyML. So Didem is going to talk about the general tinyML and I'm going to talk more about the Swiss branch, but I let you start, Didem.
Okay, sure. Thank you so much. Big warm welcome from me as well. I am Didem Attention.
So yeah, you need to take the big one here.
Yes.
And just point it towards the.
I just use.
You prefer?
Why not?
You want me to just?
Okay, this way.
So it needs to have a path to.
Absolutely, thank you so much. So I am not going to go through the agenda. I hope you all have access to that, but if I may start, well, let me just go with this one. A few words about myself. I joined the board of tinyML Foundation in January. My background is about 25 years in disruptive technologies, last 12 in AI. I was privileged to be part of Microsoft's first business AI team within Microsoft Research. Then we incubated the first algorithms for enterprise, and as those became successful, they are now known as Power Platform. You may be familiar with it. My team and I moved to AI engineering and then all the way to sales, focusing on their largest data AI engagements. Maybe it's also worth mentioning this was a derivative, basically Copilot suite. The OpenAI partnership was something I helped with after the first $1 billion investment. So had the fortune and the privilege to be part of the generative AI journey of Microsoft as well. Something that's extremely important to me, and it's genuinely an honor for me to be here at the AI for Good Summit, but also our workshop today is responsible AI and inclusion. Social impact is extremely important for me to simply sleep well at night. And for that, I have led the operationalization of responsible AI at Microsoft sales organization, Accenture, and also Schneider Electric most recently, where I was leading their AI strategy, generative AI strategy and innovation. Today, I am helping Goldman Sachs asset management portfolio companies on their generative AI journey, and absolutely pleasure to meet you. If you have anything I can help with, on those fronts as well, whether it's inclusion, girls in AI, or diversity in these areas, very, very happy to help. So I don't think, well, just so we are all on the same page, I think many of you in this room are already experts in this space, but I don't want to make assumptions. My background comes from cloud AI, so I am absolutely on a journey to learn more about edge AI and tinyML. But I couldn't be more honored that Evgeny, our chair, reached out to me back in January to join the board, because already we were hearing about AI handsets from Apple or AI Surface PCs from Microsoft, and we are truly at a pivotal time. I mean, all this, yesterday I was at the AI governance sessions here, and we were all hearing about how not inclusive, how elitist the current AI ecosystem is. And being in that kitchen for 10, 12 years, I can say that's absolutely right. It's just mind-blowing how such a small group of people, group of organizations, and this is the true democratization of AI. That's why I couldn't be more proud. I couldn't be more honored to be part of that journey. And I mostly thank you for your interest to carry it to the edge. And for those who may not be familiar with the term tinyML, it is all the way at the edge, basically, embedding AI, embedding ML into low power sensors, cameras, and very small energy devices. And we are truly grateful to people like Martin, for example, the semiconductor industry, the connectivity and software providers for bringing all this together. And moving forward, I do want to say, I'm sure some of you, if not all of you, have followed the last 2 weeks' news, right? OpenAI came with their announcements, then Google came with their announcements, and last week at Microsoft Build conference, Microsoft announced their latest Phi 3 family, which is now one of the members of that family is multimodal. Multimodal generative AI is available in this, and this graph I wanted to share that it's really fresh off the oven, if I may say so, because it shows how powerful these small language models are right now. And this slide, when the team gave it to me, it was saying generative AI is coming to the edge. No, it has actually arrived. It is very much here. So these models, of course, are operating on solar or battery-powered sensors. And I should also mention observational learning is something very, very interesting. I think it will allow us to reach SDG or other amazing noble causes, but it also means we need to be so careful about responsible AI. I really want to, because now, I mean, the genius, yes, it has been out of the box for almost 2 years, especially after the ChatGPT announcement. And yes, I was there cooking those things, but we need to stand up as citizens, just like, you know, protecting democracy, we need to protect our rights and how this technology is used for the good. I also want to mention a case study. So today I'm going to give you an overview about tinyML Foundation and just 3 taster case studies from what our amazing members have done. But I also wanted to share something that's very close to my heart that was announced last week again. Khan Academy, an excellent example of AI for good, I think, especially in EdTech. Khan Academy and Microsoft announced this Khan Miga AI tutor, which is allowing students and teachers to embrace this technology with small language models and genuinely encourage critical thinking. It's not about how can I cheat, how can I copy paste. It's genuinely about this interaction enhancing the learning experience. The AI for good part in it is they are giving it free of charge to all students in the US. And I do think that will uplift that society so much. We're talking about that. And of course, I'm also sorry to say it probably will increase the distance between developed countries and developing countries. Anyhow, that's not our topic. So who's tinyML Foundation? I would love to speak, and the more I learn about tinyML, it's just, I met them at Schneider Electric when I was the AI strategy and innovation VP, and we were sponsoring them because I had a team, embedded AI team, and it was perfectly aligned with our mission. But the more I learned about them, the more I genuinely appreciate and am impressed. So this is basically a global growing community of very passionate, very collaborative people, from hardware, software, and systems integrators, designers, product managers, and you name it. And of course, business people too. And we have more than 20,000 members. Of course, in-person summits and online webinars like this one. But I should also mention the content. We are now, as the new board, we said we need to tell our story better. What do we stand for? And we now have a new executive director as well. We're going through a marketing kind of refresh. So the website doesn't do justice. The content there is incredible. I mean, when I look through and through, it's just phenomenal content. And I think that's why we have more than 12,000 YouTube subscribers and much more, in my humble opinion, importantly, we have more than 100,000 students taking these tinyML courses. Huge thanks to people like Marco for enabling these online and in person, and especially in developing countries. This is exactly what the world needs in my view. So, and of course, I should also mention the Schneider Electric's, ABB's, Sony's, etc., the large corporations that are sponsoring these efforts, more than 100 of them. I'm going to just put this wheel all through. So who are they? The first bucket is semiconductor, software, and device companies. And of course, these executives bring in the state-of-the-art, the latest advancements. And of course, we are very grateful for that. They also bring in partnership and business development opportunities. I was lucky to be able, welcome, take any seat. I was lucky to join the San Francisco event last month, and I couldn't be more pleasantly surprised. I mean, of what came out of that. Just me alone, incredible. And then we have also, of course, that the big bucket I mentioned the names, right? ABBs and so on. Then the solution providers, I also met companies like IBM, Capgemini, and so on. And they do connect, they have this access to real world end users and the solution needs, who needs what. And of course, access to talent, very, very important, right? Especially in this space where there's such niche. We have also startups, scale-ups, and nonprofits. That's why we are also here, which is fantastic because they truly bring the voice of the end user, which sadly doesn't happen as often as we would like in technology world. And of course, they also bring in their wonderful projects or challenges, problems to solve, so they can find sponsors, talent, and partners. We have governments, of course, elected officials, which is absolutely fantastic because we need these amazing people to lead with regulation the right way. And I am literally looking for those individuals because we need them. I mean, we need to catch up in regulation. So they are so much welcome. And of course, universities and students add so much color to our whole ecosystem. I think the wonderful thing for students especially is they're able to find mentors, they're able to find career opportunities or internship opportunities, absolutely fantastic. I think some part that we will add to this, it's missing on this slide, is investors, private equity, venture capital firms. I was going there to San Francisco with a tinyML hat, of course, but then I met so many amazing companies, 5 or 6, I literally recommended back to Goldman Sachs. Why not? I mean, it's all about creating opportunities for all. So case studies, and again, let me just speed up. fabulous case studies, and I know I'm not going to be able to do justice to these, but basically the smart bird feeder is a wonderful educational tool that allows these primary school kids to detect the type of species, the bird species, enable it for optimizing feeding schedules, and also protect them from predators and pests, like it's because it's able to detect non-bird animals like squirrels or cats. So absolutely phenomenal one. And of course, such an interactive, it detects humidity, temperature, adjusts the feeding accordingly. So in winter, it gets more food, for example, for the birds. The second one is another amazing case study from one of our members. I think these are actually university students for healthcare. As some of you may know, unfortunately, 450 million, I didn't know this, but 450 million people suffer from this on average in a year, and 4 million die. I don't even know what the number was with the COVID situation, but basically this solution allowed, and it normally takes 1 to 3 days to detect this with the help of X-rays and doctors. So these students enabled a tiny device to learn from the historic X-rays and detect it with higher accuracy than doctors and do it in less than a minute. I mean, that's mind-blowing, especially in countries, developing countries where medical resources are limited, doctors are limited. I'm just amazed. The last case I want to share, and this is from hundreds, if not thousands of case studies, so please feel free to go in and check our YouTube channels or websites. Basically, the bee problem is apparently 30% of bee colonies are lost due to theft or weather conditions or damage or conflict between humans, farmers, etc., which is quite shocking. And this solution basically helped, it's called iBees, again, embed AI in the hives, and also they will have a mobile app for the beekeepers. So the beekeepers can immediately, through the weight sensors and temperature checkers, etc., embedded in the device, they can immediately act on it and also know when to harvest the honey and so on and so forth. They get SMS notifications as well as app notifications, and we're able to save. So if you're not already one of our members, I would strongly encourage you to join us and explore. We have a fantastic event. I think the next one, EMEA Summit, is next month in Milan, but also others. We would absolutely love to have you. And of course, if you would like to have a more formal relationship with your organizations, we are very much open to that as well, whether it's a technology company or NGOs or academic institutions, please reach out to any one of us. Thank you so much. Any questions we can help with?
Very much to them. So, this is an extra slide, is it?
Yeah.
So you get it twice.
There.
2 for the price of 1. Okay. So the reason I'm here today is I'm actually going to talk about the Swiss side, the Swiss tinyML group, and I'm going to push even harder that you come and join us, basically. And I think Didem's done a great job in explaining why tinyML is important and some of the great work they're doing. So I'm working in different places across Switzerland, but CSEM, EPFL, I work as a board member, and I'm also helping some startups, doing some embedded AI, and also even making sources, because we don't need just the chips, but we also need the sensors to be low power. And the reason I think we can say that it's a good fit for Switzerland to have the tinyML Foundation here is because, you know, if you look at our watchmaking roots, we see things that we have a long experience in microelectronics. We also have the RISC-V. Here I show an imager, ultra low power imager of less than 1 milliwatt. And I shout out to CSEM, a company that I'm working with as well, who did the first embedded convolutional neural network just 18 months after LeCun made it at Bell Labs in 1997. So we have a history in Switzerland of doing tinyML. And some recent work as well based on safety and security, which I'll come back to. So I want to open up the minds of tinyML and say, okay, we're here at the conference today for tinyML for good. But tinyML is really everywhere, and we really need to seize the moment and the opportunity to use it. And the first example I want to give, oops, this is going to be a bit painful. Okay. If I have the animations on. But one of the first things I want to say is that high speed is extremely important for can be extremely advantageous for tinyML. And you might think, well, tinyML, why is that useful in industry? Come on, there's loads of power in industry. You don't need tinyML. Martin's thinking it straight away because he hates when we go to high power. And I give you an example here where tinyML could be useful in industry. So the lonely spring, okay? Nobody cares about springs. You have springs all over in what you use and what you do, and you don't care about them. But I tell you, in industry, when a big spring goes wrong, that's a problem. It's costly and nobody thinks about it. And a typical tinyML case here is to make an energy harvested intelligent device inside each spring that can measure the wear and tear through strain, acceleration, and temperature. And you see tinyML has its place really everywhere in industry. So we need to think about this industry IoT. It does exist. And if we really want these sensors to be everywhere, we need tinyML to do them. Another example that we often talk about is always connected devices, more autonomous. And an example, we're going to have a nice talk this afternoon by Mathieu Lemay, who will talk about some of the measurements of the vital signs. But we want energy efficiency in all that we do. Last night, I always forget my Apple Watch to charge. It's so painful. I can't believe I'm still having to worry about this. And it's like, how are we get there? But I want to bring you back to another point, which is the democratization that Didem talked about, because tinyML doesn't only bring convenience in terms of low power, but it also brings a democratization in the knowledge. And I give an example here of MachineMD. It's a lovely startup coming out of Inselspital, sorry, my German is awful, in Bern. And what they're doing is they're making, using a VR headset, a neurological detection device to see if you have a brain disorder. And here, the AI, which is important, is that we can take the best neurological expertise in the world, and we can roll it out in this, by the way, is a Vario headset. It's a standard AR VR headset. And using this knowledge of these experts, we can then make devices that can really be exported to everyone. So it's a democratization of medical care. See, and this is where we can really do some good with tinyML. Another thing, actually, that was alluded to yesterday by Professor Qingdong Yu, who's the agricultural minister of the UN. And I thought he was very good. It's all very good, he said, all your ideals, but without food, forget it. And I thought it was a very good point. So the problem and the result that we have with food that people forget about is that we are so efficient at making food. It is so inexpensive. But it needs to be even more efficient, and it needs to be we need to generate even more food. And not only do we need to do that, but we need to do it now sustainably. Okay, so the question is, how do we do smart, precise farming? We were talking before, there's a great student over from the US who was telling me he was doing some water saving measurement to be able to do this accurate farming and precision farming. And this exactly is where tinyML comes in. It needs to be inexpensive, and inexpensive means doing it at the edge and doing it low power and treating the data at the edge, because all of that data has an expense, sending it, storing it. And as we say, if it's not useful data, it's noise. So you need to be treating this at the edge. So this is another example. And I give, again, a very simple example in a silo, checking things like humidity, temperature, opening it up so that actually these can sometimes explode. If you're not careful, they get too hot, or they can rot if they get too wet. So this is a constant monitoring, truly low power. You leave it there and it just signals if something is wrong. Okay, the final example, I tried to be realistic here, okay? So I could have put like an ideal family, but this is us, right? When we're at home and just having a chat but we want to be taken care of as well. And our homes nowadays can have the intelligence to help us, and also in a way that we're unencumbered. Because one of the things that we don't always want to be wearing a device or checking our finger here to check that we're okay. And a smart home also allows privacy in the tinyML device, because when it treats your data locally, you can have control over that. And so this is another great advantage that you can get from tinyML. Now, I have here an example. Oh, hold on, let me go back. I'm going to show it to you because I find it so funny. For Engen. Engen is a, let's see. Yeah, okay. So this is a truly tinyML device. So it meets Martin standards of like less than a milliwatt. And here what we see is basically an emotion detection. And I just want to put this out to you because it shows a little bit the complexity of what you need for a truly tinyML device. You need to have a tiny so you can see here, by the way, just in case you can't see, he's got 4 emotions: negative, excited, positive, and calm. And I think he does it rather well. But to make this work, what did we need to do? Well, we needed to have a very low power imager, less than 1 milliwatt. But we also needed to have a smart accelerator chip, which could use hierarchical computing. So first, if there's no movement, you don't turn it on. If there is movement, then you need to see if there's a face. So use a binary decision tree, super low power. Then if there is the face, you say, okay, I really want to see whether he's grumpy. And then you turn on your convolutional neural network. So it's a hierarchical, intelligent way of looking at this. So you see the complexity of making a truly low power device. And I brought one here for anyone who wants to try it. There's also one down at the CSM booth, and you can play a little video game with it by changing your facial expressions. It's quite fun. So the point of this is that at the tinyML in Switzerland, we're trying to meet some of these challenges. And when we think about these challenges, the fact is we have some people who are from the software and they're only worried about accuracy. We have some people from the hardware and they're only worried about the costs. And we actually need to bring them together. We need to make something which works. And to do that, we need a bit of standardization. We need a bit of also integration and also benchmarking across the different devices. So we have these tinyML events in Switzerland to look at on-device learning and to get the 2 groups of people coming to talk together. And I would invite you to come and join us in tinyML Switzerland. So we've already had events in Geneva, Lausanne, Neuchâtel. We've got one soon coming in Zurich and Lugano for the autumn. But maybe someone here is from Bern or Basel or your town. I don't know where it is, but if you want to come and have a tinyML, we would be delighted to go there. The next one that is already going to happen is on the 24th of September. Mark it in your diaries. The good thing about these is we don't have, not that this isn't fantastic, but we won't be sitting here talking to you at these like this. Everyone comes, they bring one device, one slide, they present their slide at the beginning of the evening, and then you walk around and look at what people do throughout the day. So it's and there's an apéro. This is us. So if you want to join, you can join via the link. And thank you very much for your time. So we're going to move into the first session. Yes, thank you. So let me see if I think you're moderating this session. Okay. Oh, yes. Okay. So Marcus. Hello, Marcus. Please come up. Marcus is from the tinyML community and is going to start by giving a sort of overview and teach us a bit about tinyML, so that for those of us in the room who don't have the experience, he will be able to bring us up all to the same level.
Yeah, I hope so.
Thank you very much.
Thank you very much. Yeah, I'm Markus Rieck. Like told, I'm a researcher from Germany, the Research Institute, and one of the founder of the German tinyML group. And yeah, currently doing my PhD in tinyML, so and especially in the on-device training, so how to train networks on the device or microcontrollers, FPGAs, and so on. And yeah, today I want to give you a small overview about tinyML, how to use it, what for hardware is there, which software is there, and how to bring it together, what's the workflow. To be honest, I don't have any clue how the title is coming in, but yeah, this is I told you what I want to show you about today. Yeah, first start with a really management overview about what tinyML is. So tinyML is, instead of the normal AI, normal machine learning, is running on embedded devices. So often, like ChatGPT or other use cases, they're running on big calculation servers. Yeah, like Microsoft Azure or Google, Amazon AWS or whatever. So really big servers. And yeah, Edge AI or tinyML is running on the device. So on microcontrollers like ESP32 or on FPGAs or yeah, ASICs, whatever you can imagine. It's really small and low power. The advantages of tinyML is, of course, the privacy. We heard about some use cases in the health sector, for example, or when you have the AI really on your home. Not everybody, and especially we Germans, we hate to send our data to servers. And yeah, maybe other people have the problems also. And so privacy is a really important point in which is tinyML good for. Because data stay on the device, data must not send on some servers. Same is, of course, the device can be standalone, so we doesn't have to communicate a lot or sometimes no communication. We can have a smaller latency because we doesn't need to communicate, and it's really energy saving. This is a really big point, the energy saving point, yeah, because communication always is really expensive when it comes to embedded devices, to IoT devices. I think in a normal IoT device or average IoT device, more than 50% of the energy consumption is going on the communication. So when we can cut this consumption, we can have a longer device, the device running longer. Yeah, and one really big advantage, we heard it on the talk before, is that it's really inexpensive. Embedded devices are low cost. We can have a microcontroller for less than $1. We can build use cases, applications, really low cost. We can bring it to every industry. We can bring it to every country, to developing country or developed country. So this is really low barrier when it comes to the cost on tinyML. The applications of tinyML are really wide. So to be honest, I can't imagine an industry or a field where tinyML is not be usable. Here are some examples. For example, you can have personal assistants like Siri or from Amazon Alexa. And you can have in the industry maintenance use cases, and so to make a production more efficient, more better. We can have really AI for good use case like the wildlife tracking. You can bring it into the healthcare and the ocean life conservation and detection of crop disease. So really, to bring it in the precision farming. Let's talk a little bit about what do we need. What is it to make some tiny use case. So we heard it before, tinyML is to combine two different worlds. So in the one world, we have the software engineers or the software, and on the other side, we have the hardware. And this is not really easy or not always easy to combine because these are different worlds. On the one side, we have guys which buy the terabytes of space in 1 second on a cloud. On the other side, we have guys who say, okay, 200 kilobytes, maybe 1 megabyte, this is everything I have on the device. And this is everything I bring on the table. And this we need to combine. And therefore, we need to have good processors, maybe machine learning accelerated processors, like GPUs, mobile GPUs, FPGAs, ASICs, or digital signal processor. Then we need, of course, something up around the calculation device. So we need a development board. We need something we can connect the devices, memory, and so on. So therefore, we have, for example, the Core Dev board. We have USB accelerator from Intel, Nano Compute 6. We have the Arduino Nano 33 BLE, and so on. There are really a lot of devices. And the good thing is, a lot of companies bring more and more devices. It gets more and more different specific, more specific or really general purpose devices on the market. Then to program these devices, we need, of course, some software tools. And there we might make really big jumps in the last years also. We have pretty good machine learning compilers like TensorFlow Lite or TensorFlow Lite microcontrollers. We have OpenVINO for FPGA use cases. Edge Impulse, which makes really great work as a startup to have the whole pipeline from data collection to compile it on a device, which is pretty impressive. And so there are more and more frameworks which are coming on and which are really important to make an efficient machine learning model. And of course, we need some support things when the device is running, like documentation examples. We need data sheets, we need standards for data sheets when it comes to, for example, new sensor types, which machine learning, we need to think about how we can write it down in such a good standard that everybody can understand it and everybody can use it. Yeah. What does the workflow look like? So the normal machine tinyML workflow is not that different from what the beginning is like the normal machine learning framework. So first of all, we need to train a model, of course. This we can do with the normal frameworks we have, for example, TensorFlow, PyTorch, or whatever you want to use. After, you need to optimize, and this is a little bit more specific in tinyML. We need to make the model smaller. So we doesn't have the memory or the calculation power to have a big model on a small device. This is just not, this will not work. So there are such tools like pruning, quantization, noise distillation, and so on to make a big model a lot smaller. After we have a smaller optimized model for the embedded devices, we can convert the model, for example, TensorFlow Lite. We made a .h file out of it or the HDL code, and the last point is compiling one really on the device. Now let's talk a little bit about the challenges of the different steps and what are solutions or research directions. When it comes to train the model, big challenges are for embedded devices are, of course, we need less parameters. We can't have 80 billion large language model on such a small device. We need to make the model smaller. We have less parameters. We need smaller architecture and we need non-complex architecture. So when it comes, for example, like to LSTMs, of course, it's possible to bring it on an embedded device, but it's a lot harder to make it on such other devices because the part of parallelization and the calculations are not that complex like on really general purpose units like a GPU. Solutions for this or research directions, if you're interested, you can dive deeper into the buzzwords. Of course, tinyML architecture search. This is a field where researchers really look deep into which architecture run good on devices, which architecture are small, low power, and of course have a small memory footprint. And knowledge distillation is also a technique or a field of research where we can make bigger models, where we can have a bigger model and make a smaller model out of the bigger model, or train the smaller model with the bigger model, which is really trending in the moment for small language models and really promising. Yeah, when it comes to the challenge of the optimization for models, we have the problem of the compatibility. So we can't have, for example, float 64-bit models or more precision models on a 8-bit controller. This doesn't work. We need to look about the supported bit size for the target device. We need to have flexible hardware. So what if when the model change? Is the hardware possible, or is it possible to change the model of the hardware? So we need flexible hardware for this. And solutions and research directions. One thing we heard about this was, for example, the open source hardware like RISC-V, which is really important, and I think we'll get more and more bigger in the field of tinyML because we can make really fast specific solutions for the use cases, which are flexible, which is really, really interesting. And we need to have a deeper dive into the hardware and software co-design to make really hardware which is optimized for the software which is running, to make it even more low power and smaller. Yeah, when it comes to the challenges of one tinyML model, so yeah, now we have the trained model, we have bring it on the device, and now it runs on the device, it's happy and everything works. But from time to time, the data change or the model maintenance. We have drift detection. We need to collect new data to make the model more stable and so on. And therefore, we need more solutions and dive deeper into the tinyML ops, which is pretty important for all the points in below. And one of my favorite research topics is the on-device training. So how we can maintain the model really on-device, so to make it really cloud-less. Cloud-less solutions. Now I want to show you some small use cases from our research institute, from my research group. You can see that it's not that hard to make a prototype of tinyML use cases, and that it can really be used for good, and that's really easy. So the first project is called Impress. There we make a soft sensor with tinyML, which brings more efficient washing machine. So industry washing machine and washing machine at home. So more efficient in case of water and washing powder. So because it's really hard to measure the tensite concentration in the water of a washing machine, we just developed a smart sensor which has an input steps, the pH value, temperature of the water, and then we calculate as the output of this model the tensite or the washing powder concentration in the water, and if we need to add more water or less water, and so we could bring down the washing powder consumption of the whole process more than 50%, which was really impressive for this use case. Then the other use case is the energy efficient detection of arterial fibrillation based on ECG data on the ASIC. So there in our group, we developed an ASIC which is based on decision trees. And we want to detect if there's a problem with the heart or not. So a medical device which can be really implemented on the human body. Because it's so low power, we only need 45 nanojoules per classification, which, to be honest, I don't have any clue what it means, but I know it's 1/10,000th of the butterfly ring of energy, and this, I think, is really impressive. And here you can see tinyML could be really, really tiny and really low power for a really interesting and good case. And this is, the news project which just began this month, but I think it's really impressive and really attack the AI for Good conference. It's called UltraSafe. Here we, let's begin a little bit forward. Researcher found out that plants can cry. So they make, in the ultrasonic frequency, they make sounds when they have too less water, when they get pruned or cut, or they have any other problems. And the problem here in this, or what the researchers have, the sensors are really, really costly. So the sensor to detect the crying of the plant costs more than 10,000 euros, or $10,000 more or less. And this is way too expensive to use it really in the industry or to bring it to developing countries and so on. And in this project, we want to make MEMS sensors because our research institute is based coming from the MEMS side, and we're producing MEMS. And so we want to make a really specific MEMS sensor with AI or integrated with AI to detect the issues of the plants, and which are really specific for this use case, which is low cost and low power, to give it really to the industry to make it visible for everybody. Yeah, but like I told, this really starts this month. I'm really, really interested what will come out in the next 2 to 3 years. So yeah, this is more or less the end of the presentation, and I to summarize what my main message is, that tinyML had a lot of, this is very useful, and we can use it really everywhere, in every use case, in every industry, and it have a lot of benefits. But we have, of course, some challenges of tinyML. We have big problems like the memory, like the calculation effort. Of course, the data is always a small problem when it comes to machine learning. But on the other side, it's really easy to make some small projects with tinyML. It's not costly to start with tinyML. There are a lot of frameworks, there are a lot of tools which help you, which assist you. And here's really easy the workflow, how you can do such a project by your own. Try it if you have an idea for your company, for something good. Try it, find people in the community. We have the tinyML community, join in, make projects or bring up your ID. Marco will talk about other projects you can join to bring something good, some good use cases with AI. And I think together we can build really cool use case, cool, interesting project and make the world a little bit better. So yeah, thank you very much. And if you have questions, feel free.
Yeah. Thank you, Marcus, for a very interesting presentation. I would like to know if somebody wants to get into the field, what would be let's say the first touch point to get into the field of tinyML from your experience?
Yeah, of course, I need to say this as a co-organizer at the tinyML Foundation would be a good starting point. And then when you're really in the beginning side, there is a pretty good Coursera course from the MIT, from VJ. This is a good starting point. Or tinyML 4D is a homepage you could really go directly as the first point. Then we have a lot of course materials bring together. Marco is the leader of the group. And yeah, there we have really in a lot of languages, different learning materials from different starting points. So if you're a software engineer and you want to go to embedded devices, you can start there. Or if you are embedded engineer, you can jump to the software or machine learning side. Yeah.
I guess we have a bit of time for more questions actually. The next session is planned at 11. So anybody has another question for Marcus?
Yeah.
Thanks again.
Maybe find out why the slides are advancing automatically.
But we had one more question.
Yeah, so again, as a starting point, I'm on the software side. Where do I get the chips? Where do I buy them? How do I start on the hardware side?
On the hardware.
I can cover that.
Yeah. I hope I say nothing wrong, but it's really easy to buy, for example, Arduino BLE. There's a really good education kit. It costs, I think, $20, something like this. It's really inexpensive. Then you can start with Edge Impulse, collect some data, and make it really easy. I think you need less than 4 hours to make a speech command use case, which thank you very much, Marco. You're the best one. This is inexpensive. Yeah, this is a really good starting point to get in touch with hardware, to talk on hardware with sensors, to bring the sensors, connect the sensors to the machine learning model. Yeah, this is one of the best starting points, I would say. And then you can dive deeper, make your own boards, make your own FPGAs, and so on.
Thank you.
Yeah,
just like getting on to the starting point thingy, how does an NGO get into this tinyML movement and get itself involved in that things, apart from the software and hardware, the use case and the immediate movement?
Yeah, the use case, it's always a good question. In my work, I do most of the time workshop with companies to find use cases which are sustainable for them, which have a benefit with them and for them. I would say a good starting point is to talk with the techies of a company. They have always good ideas, and yeah, and then look, for example, in the tinyML Foundation, there are a lot of talks about use cases, or we have a show and tell in the tinyML 4D group. There you can see what other makes, and this is always a good starting point to look, okay, what are they doing, what are they doing, and then maybe you find the transfer and, okay, this is similar to our problem, or maybe we doesn't have the problem before, but we can make our product or whatever, the process better, and you doesn't know. So yeah, such a conference is always a good starting point also to find good use cases and yeah, get in touch with experts.
I can add to that. Actually, we are always looking for challenges for good. So you can get in touch with anybody at the tinyML Foundation, by email or at these events, as Matthew said, because we are looking for challenges to submit for the tech community for them to solve. Because I mean, the community really like to solve problems and get their teeth on problems. So if you have something to propose, or you have a precise idea to what to submit to the community, then you're welcome to get in touch with us.
Yeah, I think this one was the
Oh,
next
look,
one.
I don't mind waiting. Well, anyway, so I'm kind of like wondering. So I'm like jumping into tinyML like today, basically. So I'm kind of curious about like the kind of cost and benefits. So here, like just as a quick example, you were saying like energy saving and less communication. So by what percentage would you be reducing that compared to like classical IoT like devices? And also like what is the cost, as in like is there a cost of, well, because you're transferring much less information and like the onboards like ML models need to have a certain like restricted size, like how much like loss in precision like would you, for example, get compared to like more powerful things that don't need to be embedded like this?
Yeah, I need to give you a student answer. It depends.
You know what? That's my fault for asking the questions.
It's yeah, it really depends. When you, for example, imagine you have an IoT device which have always on a microphone, and you send the microphone data every time to the cloud, then you can calculate, yeah, you have 160-90 kilobytes per second on data which you send to the cloud, and audio is, yeah, really low cost when it comes to memory. When you imagine images, then you have really big data which sent 24/7 on the cloud, which can be really expensive. And when you, for example, think about a smartwatch, when you make all the classification which is on the smartwatch, when you would send everything on the cloud, the smartwatch, I see a calculation would the battery would could stay 5 minutes on. So when you send everything on the cloud, so this is that expensive. But because there's a lot of on-device calculation, really efficient and really smart on-device calculation, it's yeah, 24 hours at least on the device. So yeah, it depends really on the use case, but yeah, I think Google Alexa, Amazon Alexa, or the smartwatch is a good known example how important is good pre-processing on the device. And when you want to send really data on the cloud, you can do this. But with tinyML, of course, the best case is to do really everything on the device.
I guess we have the time just for one last question, and then we just take 3 minutes break. I guess everybody get some fresh air.
Your coffee? For sure.
And coffee.
Coffee.
Yes, I'm a newbie as well, but keen to understand whether you've had any success with sign language at all, which is a visual language, so not based on text, so quite unique in that the data is a 4D vector effectively.
Yeah, so there is already a few models available, but these are mostly large models. It's still let's say a challenge for the AI community to very well translate sign language to spoken text or written text. So this is still quite a challenge. There has been efforts, but I haven't seen yet a product built out of tinyML.
It shouldn't be that hard. Huh?
That's what everybody says.
No, but the problem is hard. It might not have been addressed properly. That's the only open. I don't know. But
No, no,
shouldn't-
it-
there's-
Image data is heavy.
Yeah, I guess the data is.
Image data is heavy.
Data sets are tiny by comparison to spoken languages. I mean, you might correct.
So I would say the first step is maybe to solve the sign language
Yeah.
in ML
Yeah.
as a problem, and then you can optimize it towards that would be my approach. Because if you don't get it at the ML language, machine learning language, then it's even harder to get it on these constrained devices.
Also, if I can add to that, one of the big issues was data, which you just pointed out there, that the data set is rather small. But in the eye gaze example I showed with the neurological, this is now, we're getting more and more data through data generation. And these models have really come very, very far. So before, where we would always spend at least 80% of our resources on the data campaign, now in this one, we used like 1 million images, but completely synthetic, which gives you also the ground truth of what they're actually signing. So that would be also something I would do. I would start by making synthetic images from which you can train. I'm happy to talk to you about
I'd
it.
love to,
how
thank
to
you.
do it. Okay, so 3-minute coffee break?
Yeah, 3 minutes.
Yeah, so
Yes.
And if you're interested in proposing a challenge for an NGO.
Yeah, like.
Take your,
let's say I was relaying this conversation.
Very interesting. Not really an NGO, Yes.
Wow.
One of the challenges you have.
No.
Like whatever she tries, I need to like get out.
Yeah, this is for a training course. Yeah.
Yeah, and we will see if in this session and in the following session, actually tinyML and Congress. Helps kind of make my job like. And they do very much medical grade. There's a big difference between the wellness sector and the medical sector. It's very much the medical sector. And I think Actio, which is this blood transfer monitoring and the rest, came out of this group.
Yeah, there's only about 300
Just get a coffee. Is it right there?
There's no tabs.
I have a presentation data. Okay, because I will need the
Oh.
Very
nice.
Yeah, the reference and
Yeah.
you have everything.
Nice resolution.
Matter of weeks,
Transcript, yeah.
Didn't go to public broadcast.
Okay. So, yeah, now for development. Now we're.
Sign language.
There's been lots of attempts. It's actually being used by the different.
You know all of these, sign aloud.
I know lots of them. Yeah.
These are not robust enough to read.
So we loaded out onto the technology is here. It's just well negative.
Make it. Problems always the request, the market. Is the market.
Worked on selling.
But I think technology is keeping it.
If it's not that,
It's
So we
another.
provide, we've got 6 data set, sign language in the world now.
Then maybe it doesn't.
Translates
But I have
There's a
my lab is working on
sign
sign
language
language.
websites.
And
for
it's
Bank.
great.
And so you need to have a lot of like
So
deployed
we've got 7
and
things
there's are
the one sign language English, not sign. But
And you
we're running out
cannot
of deaf talent
send
really
like
quickly because there's only 37.
Yeah.
So this is why one of the drivers behind next the automated sign language. Yeah, it is hard. But I'm sure it's possible, like you said.
At least.
I hope so.
Like a tinyML challenge. Because it's only cardiology, is what I really like. MIT has open challenge every year. There was a challenge based on how to classify everything
On the net.
Pushing the,
Citizen data is different with sign language because
Yeah.
That's when it
will vary so much. So we really want to train the model of qualified translators in the first instance for it to be useful to keep the standard really high. Otherwise, you just get people jumping on that know a tiny bit of sign language. So we like to try and capture the data from our translation team and produce digital twins. We've got a project starting. Microsoft have got a symposium in the autumn where they're revisiting the whole
Yeah, I
data.
feel like there's two.
Everybody needs to get together.
Boy.
So I think that
Right now I love it.
and they their sign language.
Yeah, so we're that, well, it doesn't, money is coming in 7.
Well, yeah.
they are at least more than the usual.
I feel immense guilt.
I'm not sure about time.
This session is worth
Having resources and stuff that they can load.
Yeah.
Portable,
Cozy to cuddle.
Comment c'était cette semaine?
Are you in here all day then? I am gonna be, I'll tell you between this session and another one. Yeah. But I'm gonna get some.
yeah, so I mean.
I'm from
Organizations like disability rights at the state. But it's 100% powered by human intelligence. So, and we're training young people as young deaf people as translators. It's all really good, but we're going to run out.
Exactly, right?
And we haven't got the money to train them. So, yeah, to start. So you get the signing easy while we train them. So you in academia? Okay.
So, I'm here because I did my master's thesis on tinyML.
Okay.
Just finished last summer.
Yeah.
Currently trying to reorientate
Other
my
progress
career.
in
Right.
Mechanical engineer working as a program manager.
Yeah.
I want to make use of my
Yeah, basically.
skills.
I'm sure you'll find something really interesting as well.
Yeah,
What a
so,
fascinating field.
yeah, and I've been working on image classification on time sensors.
Okay.
And that's why I came across all the sign language stuff during my research phase.
Brilliant. Well, if you've got anything to share, I'd love to see it. Do you want to take my LinkedIn details?
Yeah.
Would that be possible?
And,
Use quickest with the code. There you go. Also,
sorry, I'm not sure if we've got the code installed on my.
Hopefully that's the first time.
But also for the
Otherwise,
automatic,
they're just not here or they're there.
for the automatic, can you turn down the temperature?
Oh, yes, please. Yes, please.
Right now. Light,
That looks all right.
right, this is.
Now everyone's seen them, I don't need to present anymore.
you can just use your camera.
You don't touch too much.
You do yours, whichever, I don't know.
Oh, here.
It's quite ironic that the signal's so bad here, isn't it? I can't get on the Wi-Fi. Okay, let's see. So I think I'll do yours then. It's one moment.
That's never used to secure.
I can see it, I see the thermostat. This is only
Wait, we
the,
want to go back to the entrance.
I need to go back to.
Brilliant.
Yeah.
Right, I'm gonna go.
It's here, no?
Needed.
That's what I thought, but no, this is just,
Oh, that's the icon.
That's the light. This is it.
I was waiting for the oxygen mask to drop from the
I
ceiling.
know.
and it's like, oh my goodness.
I
Is
give
there
you-
a
I was
remote
gonna give you
control?
my-
Takes a remote control to tell them.
It came on at some moment, there was like for 10.
Take temperature,
Like,
turn it down.
There's our intelligence. Let me see if I can.
The good use case for AI on the.
There's lots of power in there.
Well, it just.
Almost that seems to just be the screen and the lights, and nothing else.
Yes, yes, I do.
Okay. Do you want me to just start like that, or you're going to intro?
Order are we going in?
I'm going for Harry.
Sorry, I was wondering, I didn't quite catch before, like where, like I could find all like the resources you were mentioning.
Okay.
Yeah.
I can.
Thank you.
Yeah, yeah.
So much.
So,
Yeah,
Can I
yeah.
watch that while you?
yeah, sure.
Yeah.
I couldn't find it.
You want to learn about tinyML?
Yes.
It's a website called tinyML.
Okay, let's
Okay.
I will present it later. but-
Oh.
Ich habe diese Woche ja schon 2 Sessions.
let's go ahead. So welcome back everyone. We will be starting our next session called Breakthrough in Hardware and Implementation Challenges for tinyML. We have 3 speakers today, and the first one is Martin Kuhn, Vice President of Marketing at Greenwaves Technologies, and he will be presenting their tech, what they do, was tinyML at Greenwaves.
Okay, thank you. So I'm going to be talking about hardware a little bit, but I didn't want to do too much hardware. So I'm going to be talking a little bit about what we do with the hardware rather than just talking about hardware. So who are we? Greenwaves is a French semiconductor startup. We're what's known as a fabless semiconductor startup, which means that we design chips and we sell chips, but we don't actually build them, because mostly there's only about 3 or 4 companies in the world that actually do very small digital chips. So we're not the builder. And our particular area is designing processors for extremely energy constrained devices where you need to do a lot of processing. We're mostly based in Grenoble in France, but we have offices in Italy, in Denmark, which is a big audio center, and you'll hear me talking about audio. And in Shanghai, we have a support team looking after our ODMs and people building products. We have very strong links with Swiss University, ETH Zurich, and with Unibo, University of Bologna, who jointly have a program called Pulp. Our CTO is one of the co-founders of Pulp, and Pulp is a project that looks at using parallelism to reduce power consumption in a lot of sides of that, chips and products. GAP9 is our 2nd generation product. We now have 2 chips. We've moved to our 2nd chip. GAP8 was our first chip, which has been in production since 2020, and GAP9 is now fully production qualified, shipping out to customers. In fact, the first products have been launched on it. Nicely, GAP9 is actually both designed and produced in Europe. It's produced in Dresden at Global Foundries, and I'll be talking about a little bit more about GAP9 at the very end of the presentation. So I was thinking that this is about good, so I have to sort of kind of break that down and then put us into the kind of big application for good thing. And obviously, you know, we make a chip, which is really at the very bottom. We do a lot of software for runtime and tools and things like that. In fact, there are more software engineers in our company than hardware engineers, which is very normal for chip companies, particularly for processor companies. But there's an awful lot of other bits that need to be there. You know, the hardware, the actual boards, the app, the tinyML models that we've been talking about this morning. Then you have to kind of like wrap that all into a device, and then maybe there's a full application with some website or whatever. And actually none of that is going to happen until you have an idea. And you actually discover somewhere where you're actually going to deliver some value to someone, either whatever that value might mean to them. Okay, so, and one gets to those ideas by imaginatively understanding problems. And imaginatively, in that sense, is kind of combining a knowledge of the problem with a knowledge of the technology. So today, what I'm going to try and do is go through some of the steps that we see in terms of things that are in the market, and give you some of the attributes of them, kind of extract the attributes so that you can start to spot maybe a problem that you have that could be solved by this. So I'll look at, what is tinyML to us, actually, to Greenways specifically. What are the applications that we focus on? What are the attributes of those applications? What are the challenges we expect or our customers see when they're doing this? So what does the tiny in tinyML mean? Okay, in our opinion, and this has not always been the case in tinyML, we believe that it's not tiny in capability. Okay, what we believe is that you have a tiny constraint, hard energy constraint on the application you're doing. Okay, and hard energy constraint means that energy efficiency is not that interesting if you're still consuming a watt when you're energy efficient. Even if you're consuming 500 milliwatts or even 100 milliwatts when you're energy efficient, because your application won't work unless you get to the energy point that's compatible with that application. And that this is where, where we are focused. So some areas where we're seeing tinyML deployment now with our chip physically in the market. So the first product is actually an announced product that's launched. So this is an over-ear hearable product. So it's an over-ear earbud, basically. So it's the one that doesn't stick in your ear. It plays music outside. Why is tinyML important in something like that? Well, one of the challenges with open ear is delivering good active noise cancellation. It's very difficult to do. It's easier when it's stuck in your ear. It's even easier when it's over your ear. But doing it on an over-ear product like that is very, very difficult. This is the first product in the world to have active noise cancellation in an open ear product. We control that with NN, combined with all the things you have to do for active noise cancellation, which are very, very complicated and difficult to do. So we have to combine the two together. So here you're combining two different types of technology, and you're seeing the NN side become basically just an element in the delivery of that solution. It's not the whole solution. There's lots of other things you need to do inside a product of that type. Other areas where we've had product shipping in space and energy management. So these are sensors that you can stick on a ceiling, which have batteries in them. Why do they have batteries? Well, basically pulling a cable through these overhanging things here and trying to drop it down into a sensor costs a lot of money. There has to be someone coming and installing that cable. Very often the companies that are installing these things are service companies that need to have separate networks, separate power, separate everything else from the building that they're installing into. Medical devices. So this is showing a smart pill. So a smart pill is clearly a very energy constrained device. These are devices that you swallow and they take a photograph as they go through your digestive tract. And obviously there's a lot of photographs that they could take, and that's going to be a huge amount of images that you have to store on the device, and there's a limit to what you can do with that. There's also limits to what you can transmit outside through the body. And there we can play in terms of both compression technologies and also in terms of actually seeing, is there something interesting to look at, and only storing that. So what are the attributes of these devices? There are really kind of two big classes. Actually, I would add a third one, which was mentioned by other people. We really don't service it, which is in sensor. It's combining something with the sensor itself inside the sensor. There are two other classes that we do cope with. And those are, one is kind of really small things that need a tiny battery that needs to last hours. And then the other side is a much, much larger battery with something that needs to last years out in the field, okay? And there's another kind of level of difference between these. Generally, the top one is doing something all the time until it's switched off. So really what you're trying to do is be energy efficient about the thing that you're doing, right? Whereas the bottom one, you're being energy efficient when it's switched off. You really want to do nothing very, 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 very well. And then when you wake up, do a burst of activity that's at a low energy level. But mostly those applications are dominated by the time when you're off rather than the time when you're on. So you're trying to limit the amount of times you're coming on. And then behind those, generally there's a network. And generally the amount of energy you're going to spend sending something over a network, particularly an image or something of that sort, is going to be very, very expensive for you. So essentially what you do is you use the neural network to stop you having to send that image, or to essentially gather something from the image, like there's a person. There's a person is just yes, no. It's one bit of information. An image is way more than one bit of information. So therefore, what you're doing is you're compressing the image down to one bit. Okay? And a lot of these applications are compressive in their nature, whereas the top applications are intensive in terms of compute. So examples, how do you use tinyML in an audio product? There's multiple different levels you can use it at, and there's different levels of complexity in each one of these levels. At the top level, you could do something like scene classification. So I listen to the surround environment around me, and I work out, are you in a bar, in a cafe, are you in a plane, are you in an office? What kind of noise environment are you in? And I react in the product to that. So I change the product capabilities because of that, okay? If I'm in this plane, perhaps I cancel noise in a different way to when I'm in a bar. It's different noise. These are generally fairly low load neural networks. They're the kind of things that you can run on microcontrollers. We kind of run them as a sort of side effect, generally. They're almost given for free on our chip, but they're very, very small networks. They're generally not real time as well. It doesn't really, you're not going to change your location every 5 seconds. You're going to hop on the bus and off from the bus, repeatedly. So these are not real time things. Then there are things like filtering non-stationary sounds, so in-call noise reduction. So if I'm in a noisy cafe and I've got people talking all around me, I don't want the person on the other end to pick that up of a microphone. And also, if I'm on a call with someone who's in a noisy environment, I'd really like to clean that signal so I can hear better. Okay? These are high-load neural networks. And the difference between these classification, 1 or 0 out the end, is that this is actually producing a filter for the noise, which is lots of really analog signals that you're trying to generate to filter out noise. And there's a big difference in doing these kind of models. They're much, much, much more difficult than the top ones, right? Then there's combining things all together. So active noise cancellation, the example that I gave earlier. There, active noise cancellation, you're trying to take a signal coming from an error microphone and generate a cancelling noise in the time it takes for the sound to go between the error microphone and your ear. There's a very small room. It's going to go very fast. So you need to do it really, really fast, the filtering, okay? But we can use neural networks to steer that filtering. And here you're combining lots of different technologies together and actually delivering something which is kind of mishmash of technologies brought together to solve a problem. Where does tinyML not make sense? Okay, there's one case which is obviously if you have tons of power, right? It probably doesn't make sense to make loads of effort on the thing being low power, right? I mean, within restrictions, right? There's ways that you don't want to expend energy for no reason, but you also don't want to expend development cycles and money on making the thing microwatts when you've got, some milliwatts. Why bother? The second one, which is a little bit more subtle, is balanced. If you have a sensor that's consuming 100 milliwatts, is there any sense of using a chip that uses 1? Probably not. Probably if you used one which used 50, you probably get away with it, right? Because you're really not changing much by reducing the amount of power that you're using in that chip. So having a balance between the sensors and the chip is very important. So then what are the challenges of building real applications? And Marcus mentioned some of these, and I totally agree with a lot of what he said, right? The first thing, I think there was a question earlier, was basically you need a workable application without the power problem, right? You need to solve the problem without power as being an issue to start with. If you can't solve the problem with a huge, machine learning model, then forget trying to make it small because it's not going to change anything. It's actually going to make the whole thing worse. So you need a practical, feasible idea. You need the training data to train your model. Okay, and as Andrea was saying, you can synthesize a lot of data now. Augmentation's been used for many years, but now you can synthesize the data. But then you've got a few problems you're going to have to get past. Once you've got your working model, you have to get it to a size which is compatible with the power budget that you have. And that's really the point. It's compatible with the platform, sure, but compatible with the power budget. Because if you don't get it to a right power budget, your use case doesn't work, because as we said, you've got a hard limit. You can't have an earbud that lasts 2 minutes. It doesn't work. Compatibility of the model with the target platform, which was mentioned earlier, and then overall kind of a holistic energy consumption of the whole solution. And that goes into hierarchical things and so on and so forth, which were mentioned earlier as well. And then you've got all of the classical challenges of an embedded platform. You know, designing on embedded chips is much more difficult than writing Python on a cloud server somewhere. It's not the same thing. You need engineers that are skilled in doing that. And they're difficult to find. And then you have all of the problems of, you know, is the communication reliable? Can I upgrade the thing in the field? Can I produce it in a way which is stable? Which is a big problem for ANC. For example, most ANC earphones don't actually do any ANC because they have too much variance. And, you know, I'm not going to sell it as easy to do. It's perhaps easy to get started, but getting real life applications like this up is not easy to do. So what applications use our application processors? So I mentioned a little bit, but we combine kind of 3 different processing capabilities into a single chip. Very low latency DSP, which is digital signal processing. So this is related to ANC. So this is being able to treat sounds very, very fast, filter sounds very, very fast. Combined with general DSP, so this is things like compressing the sound to send it over radios, codecs and so on and so forth, doing lots of different types of filtering, and then neural networks. And trying to bring all of those together in a platform where we sustain flexibility, because flexibility is super important into these applications. If we design chips, it generally takes us a couple of years to do a new chip, right? And that's quick, okay? If we design now for what's happening now, then we'll be great at making what happened 2 years ago happen very low power. That doesn't work. We obviously have to design something that's more generalistic than that and focused on actually delivering a general solution. And then easy to program. Easy in inverted commas, right? It's an embedded platform. Embedded platforms are not easy, but this is easier versus the alternatives. And then we do all of these different types of things in 7 segments of IoT, wearables, hearable products. And our product is this little tiny chip up here, which is 3.7 by 3.7 millimeters. This is a 10-core RISC-V based processor, so if that speaks to you. That combines units to do all of these different things. A smart filtering unit, which is the thing which we do all the time, streamed autonomous time domain signal processing, general digital signal processing, which we do in a cluster of RISC-V cores, neural networks, where we combine both the cluster and the neural network accelerator, which is quite unique in the market, and then delivering ultra-low power, highly flexible, easy to program versus the alternatives. And we have all sorts of tools and boards and stuff that you can use to get up with our products. Oh, one last slide, I forgot it. A chip's not enough, right? We need lots of partners because we're actually providing, you know, just the base stuff. And then we have software partners around us that actually devise things and do the real hard legwork on certain models and applications. So we have all of these guys, for example, Orasound Labs are doing a complete reference design around our chip in terms of TWS. They're in fact the guys who did the ANC in OWS. Audio Sorcery. This is a company that does voice and music separation on our chip. So you can actually play a WAV file coming into it, or even, you know, live music coming into it, and we'll separate out the singer from the rest of the instruments. And we can separate out single instruments like drums and so on and so forth. So you have an instant karaoke box, basically. People doing spatialization, IDUN. A lot of people doing different types of AI noise enhancement to make it easier for you to speak to someone, to denoise what you're seeing in front of you, to use combinations of different techniques to do that, for medical and hearing devices. And then denoisers also for doing things like I said, denoising a phone call. That's it. Any questions?
So I've seen the Gap9 process. I think it's been used also on very tiny drones in that whole project.
Yeah, they did. The Gap8 was used on one of those, and now the Gap9's being used on it. But the Gap8 one you can actually buy. It's for the what are they called? I can't remember the name of the company. Crazy Fly. Crazy Fly. They have an add-on board with the Gap8 on it, and so there you can do things like following a corridor, and it will follow down the corridor using vision processing to identify a path. And they trained that neural network, actually just as an interesting anecdote, on driving data from cars, but they also trained it on students riding around on bicycles with a camera in front of them and then measuring the angle of the steering wheel and whether they put the brake on.
Yeah.
It outputs steering angle and, oh God, there's something in front of me.
Okay. Yeah, that's exactly. Yeah. So I see it's being used in like these very miniature robotics applications.
Yeah, drones is an interesting one because actually in the Crazy Fly, the interest of it is that it's light, not power, because the engines in a drone use way more power than anything else. So my balance slide, that's important, and lightness, power, but also heat can sometimes. We've dealt with companies making over-ear things that have cameras in them, that were using chips that actually heated up your ear, which is really uncomfortable.
Okay.
And the interest of using us was to actually have something that didn't heat up. So, and didn't need a fan because that would also be, well, might be good.
Also a problem, right? So is it of interest also on the control side, for instance, to deploy reinforcement learning on these types of chips? Have you tested anything in this regard?
Reinforcement learning on those kind of chips, we haven't done that much on. There are some research papers on reinforcement learning on Gap9, but we haven't done that much on. We haven't found the right application, but if you have the right application, we're happy to work with you on it. We also work with a lot of students and a lot of PhD students and things like that. We have, if you go to our website, you'll find a whole load of academic papers that have been written about Gap9 and lots of different applications like fit detection, EEG based fit detection, tons of stuff in lots of different domains.
How many IO channels can you plug in?
Which type of IO?
EEG, for example.
EEG. Well, EEGs generally come through a D to A, A to D. So we have no analog input channels. We always use external ADCs, and actually in the application they designed their own ADC because it was very specific to the EEG signal. So in that case, it was actually a specific, because that's one of the problems with ADCs is which one, what resolution, what some noise, etc. Any more questions?
Very good, thank you.
Thank you.
Thank you. So our next speaker is Andre from Sintara, who is also a member of tinyML Switzerland Antenna, and he's representing their activity at Sintara, and especially a new type of technologies that they have developed.
Oh, and if you want to take cards, why don't we take these chairs for you? I feel a big guilt sitting over here, right? So. Seems a bit silly to have chairs sitting here.
I'm gonna stay.
Maybe the speaker has a bit more space. Sorry about that. Right.
Figured out the remote. It's tough to work on. Right, so thank you, everyone. So I'm going to start off this presentation by giving you a bit of an introduction about who I am and what Sintara is doing. And then I'm going to dive right into the problem, which is what is one of the things that is preventing us from deploying tinyML on edge devices? And that is a bottleneck that is occurring between the memory and the compute on a chip. Then I'm going to introduce a bit about a technology called in-memory computing that has huge promise. And I'm going to tell you all about it. But then we're gonna come back a little bit and do a reality check to see if it's actually delivered. So a bit about myself, to answer your question, yes, I have different ties, but this one I like. I'm a field applications and software engineer at Centara. Centara is a Swiss startup which does semiconductors. And we are focusing at the moment on in-memory computing. And my background, I have a PhD in applied AI to neuroscience from Oxford. I am on a very steep learning curve about hardware, but as you'll see, I'm not a hardware guy. And I've worked for a few companies in different application roles. This is my level of understanding about hardware. This is my friend Chippy, and I'm going to tell you a story about him. So Chippy is our embedded microcontroller chip, and he's very happy today because he has a lot of friends. He works with a lot of OEMs and ODMs, and he's very useful in a lot of applications. But as you've seen up until the talks that happened until now from Andrea and Martin, we live in a brave new world where we're having a lot of deployment of different AI applications in edge contexts. And they've done a much better job at explaining this than I can. But the core challenge with a lot of these things is that we need high energy efficiency devices to enable all these applications, from automotive to industrial, on the edge. Now, this is a problem for Chippy, because Chippy, particularly when you give AI to him and he has to do AI, he becomes very sad. There's a few reasons for this, and we'll go into them. So the first reason why Chippy becomes very sad when he has to do AI is because AI needs a lot of compute. So up until about 10 years ago, the computational demands of AI generally followed Moore's law, doubling every 2 years. But about a decade ago, around 2010, 2011, we started the computational demands of AI skyrocketing. So now we're seeing AI compute demands doubling every about 3.4 months. That's very fast movement. Now, we can solve this in two ways. The first way is we make better processors. Great. We were able to do that, but we're starting to see a problem occurring. And that problem is that these processors need to be fed data in order to operate. You need to feed that data from memory to the processor, and then you got to feed it back to the memory to save it. Now, that's fine when you're not doing data-intensive applications like AI. But when you start moving to AI, these are very data-hungry applications. And that means you have to move a lot of data from memory to the compute, which is very expensive. So that ends up clogging up the bus or the communication between the compute and the memory. And that leads to high power consumption, and that leads to bottlenecks in performance. Now, for the people in the audience that aren't a hardware person like I am, a good analogy that I found was that of a city. So you can think of the typical city. You have the city center, downtown, where you have all the businesses, all the activities happening there. And you got the people from the suburbs where they live having to come all the way to the city center in order to work. And that clogs up the highways between the suburbs and the city center. Now, how can you fix that? Well, you build larger highways. But because of a little thing called induced demand, that those highways end up being clogged up as well. What's another solution? Well, in Switzerland, good old Switzerland, they've solved this by distributing economic activity from the city center out to the suburbs. So you have businesses located across the city, which means that people don't have to travel that far from home. Am I saying this? Well, for first, it solves the traffic problem because you can use public transport now, you don't need highways. But then we can take this analogy to a thing called in-memory computing. So in a nutshell, what this does is take part of the computational load from the processor, from the compute engine, and put it inside of the memory. And this has the effect of lightening the workload of the processor because he has to do less work now. But it also saves you having to move all that information between the compute and between the memory and the compute. And this promises 100x level improvements in compute efficiency. Now you might say, Andre, okay, fair enough, cities, analogies, Chippy, all fine and dandy. Where's my chip? And memory computing is so great. Why haven't people been doing it? Why don't we see this sort of technology deployed at a wide scale? And the reason behind that is that in-memory computing is massively disruptive to the entire ecosystem. And I mean hardware, software, devices, everything. Just to touch on a few things that in-memory computing causes issues with. It causes issues with controlling coordination. So you can imagine now, instead of one processor that has to get information, you have a million small processors.
Ladies and gentlemen, the center stage of the AI for Good Summit has started again. Please go to Room D or Room A if you have a leader's pass to check out the next round of keynote presentations on the center stage of the AI for Good Global Summit. Thank you.
Or you can stay here.
So as I was saying, it can cause a lot of control problems because now you have to move information between a lot of different places, and that puts pressure on your control mechanisms in the chip. But then it causes hardware and software problems because we have been used to designing chips for microcontrollers for different devices in a specific way for decades now. How do we fit in this new paradigm inside the software and hardware ecosystems that we have at this point? Then it causes a more soft level skill with training. You know, this is a new technology. We need to train people how to use it, how to design it, how to integrate it, how to program for it. That takes time. It's a big overhead that organizations don't really want to deal with. So we're in a bit of a pickle at the moment. And at Centara, we think we have the solution to this. And I'm going to talk to you a little bit about our main product. So our product is called ComputeRAM. And without going into too much detail, it's essentially an SRAM chip, a normal memory SRAM chip with in-memory compute capabilities. And on top of that, we're coming with an SDK, a software development kit, which enables the user to translate any AI, DSP, and essentially any other linear algebra-based algorithm to work on this in-memory computing enabled SRAM. Just very briefly, so on the hardware side, we've designed this to be essentially a drop-in replacement to a normal SRAM chip. So if you have any chip which has an SRAM, you can take out your traditional SRAM and put in ComputeRAM. It has a minimal area overhead, so you won't be suffering much in that field. And the other thing is it's instruction set architecture agnostic. So it can work with your ARM, it can work with your RISC-V, x86, whatever you. The real magic happens in terms of the software stack. So the software stack allows you to run, as I said, any AI or linear algebra-based algorithm without any code rewrites on this in-memory computing chip. And on top of that, we've included libraries of optimized algorithms that can allow you to do essentially build optimized networks for this hardware from the get-go. Now, this is not a marketing presentation, so what I want to get to here is what this chip can actually do and what it can enable us to do with that. So I say, okay, we can do linear algebra. What does that mean? So let's take a very simple SoC. We have an ARM Cortex M0, we have a very simple bus, and we have an SRAM. And I want to do, on this microcontroller, I want to do some very simple linear algebra, matrix vector multiplication. As simple as it gets. And I want to see what happens if I swap the SRAM for the ComputeRAM for different sizes of matrices. And this is what happens. So in terms of latency, we are able to achieve almost 140x improvement in speed. And also an almost 160x improvement in energy efficiency. You say, okay, that's fine. Nice numbers. A nice gate level simulation you've done there, Andre. But what does it do for tinyML? I'm interested in some applications here. This is academic at this point. I'm sorry for the non-engineers in the audience. So what we said, okay, let's look at what ComputeRAM can do when we deploy it in the context of tinyML. So we took essentially in the very far left of the table there, you'll see the tinyML networks. This is the MLPerf benchmarks that are quite famous in the community. And we deployed them on a almost similarly simple system. and we tried to benchmark them to see what compute RAM can do. So the system is very simple. You have a microcontroller, you have the compute RAM, an SRAM memory that holds the information, an accumulator for doing sums, a very simple AHB bus, and you could add or not add the DMA. For these numbers, we did not add a DMA. So what we're seeing here is that at the top of the pile, we're achieving improvements of 500x in terms of energy consumption and 65x in terms of latency compared to the best reported tinyML submission. In terms of the other ones, we're achieving, in some cases, we're achieving performance improvements, in others, we're not necessarily. We're about there, but ballpark. But then we have to consider, okay, what's actually going on under the hood when we compare against different numbers. The first thing that we observed is that Sentient, which is the best performing hardware configuration for 3 of the networks, they use a dedicated accelerator for tinyML. Now, I don't know if you got it from context, and I should have mentioned it. But the idea with compute RAM is that what we want to offer is generality. So we do not want to limit the developer to a single architecture or a single set of models. We want to give as much flexibility as possible because that's what's needed. We need flexibility to develop models, to deploy them, to update them. And the other thing, this is more of a hardware consideration. In our simulation, we used a very simple bus, but we expect that with better buses, can also improve, but let's not worry about that now. Let's consider our simple configuration. Now, given that we're comparing against a dedicated accelerator, but we actually want to make a point about generality, if we expand this table to look at average numbers across all the submissions in ML Commons, these are the numbers that we're seeing. So at the lower end, at least 10x improvement in energy consumption and latency, and some very high numbers at the high end. But again, this is very general, very academic. But one thing that we need to consider is, are these networks actually designed for this type of hardware? These networks have been put forward about 10 years ago. They've appeared. And when we look at how they were constructed, they weren't necessarily designed for these sort of hardware, like compute RAM is, like in-memory computing. And we can see that when we looked at the utilization of compute RAM by each of these various networks. So anomaly detection, which gets the very high numbers, uses about 50% of available compute RAM resources. But the other networks go down to about 1% of available compute RAM resources. And that's because the way that the operations are built within these networks isn't necessarily the best way done in the best way to be able to employ in-memory computing. Then we said, okay, fair enough. Can we improve them? So we took the anomaly detection, which is already our best performing in our simulations. We did not change the hardware in any way, so still the same simple configuration that I showed you earlier. And we did an architecture search where we said, okay, let's constrain energy, constrain memory footprint, and I want to get the same accuracy at least. And this resulted in an anomaly detection network that is shallower and wider. So basically you're squeezing it. Instead of having a very deep network, you're having a shallow network and a much wider set of elements. And what we saw here was that when we're doing this improvement of the network architecture without losing any of the results, we're able to squeeze even more speed out of the setup, even more energy efficiency. And we get our energy efficiency up to about 4.5 to 9 teraoperations per joule. What does this allow us to do? So as a company at the moment, we're taping this out. So these are based on gate level simulations, but we are taping out the chip. However, we are envisaging an extremely wide array of applications. So Andrea already gave a presentation about the myriad of applications that tinyML has. What we believe compute RAM can do is enable these applications. So it can enable applications from anywhere from healthcare all the way to automotive, AR, smart city grids, efficiency in agriculture, newer, better devices. And this is what we believe hardware should be doing. Hardware shouldn't be targeting these very narrow use cases where you do one thing extremely well, but then you have the fact that you're constrained only to 1,000, 2,000, 10,000 chips, and that creates a whole lot of pressure on designing them, on selling them, on marketing them. We believe that hardware should be as general as possible and then allow developers to be creative and develop innovative solutions. And that will also make Chippy happy when you add compute RAM to it, because now you can do AI. Thank you very much for your attention. And
talking about RAM capacity, which is the capacity you are simulating with?
so the way we simulated the chip is that depending on which network you have, the simulation gives it enough memory to run. We're talking about in the order of maybe like 100 kilobytes, 150 kilobytes for the biggest networks. Actually, anomaly detection is one of the biggest ones, these parameters. But the nice thing about compute RAM is that it's plastic in that sense. You can scale it up and down based on your needs. So depending on the application, we can discuss and we can scale it and give you enough processing that you need. Or if you're in a constrained environment, then the SDK takes care of coordination and control in such a way that information and network parameters are moved on enough compute RAM to make it as efficient as possible.
Have you tried with a specific language? I mean, DSP language in order to program your memory? Do you have tried with any specific, or is it also general? Any platform for building?
So at the moment, we're optimizing for TF-Lite for micro, but we're trying to make it as general as possible.
Sorry.
Yes.
Just another question about the simulation. Was the M0 core, was that in the same chip? Was that external? When you did your simulation, did you take into account the cost of getting off chip?
Yes. So for the original set of results for the linear MVMs, in that case, we are considering the energy cost of moving information on and off the chip and on the memory. So that is modeled. For the tinyML situation, we did not consider that because that wasn't a gate level simulation. So that was based on previous simulation results, and we've adapted them. Yes.
More practical question then. You just told that you had a tape out, right? I guess it's arrived around these days or something.
Yeah, so we've done a first tape out in October, and that was a prototype of the chip that was built within an accelerator. It proved the concept that it works. And this month we are doing a tape out of the actual compute RAM chip. So we should be having the actual chip results in a couple of months.
And if I'm an NGO or a company that wants to get in touch also with you to get access to these platforms, do you have any plans of partnerships, for example, to try out these or?
Yeah, of course. So you can reach us over our website, going live at the end of this week. Or you can reach us directly via me or by our CEO. The way we market compute RAM is as an IP model. So we provide the IP, we provide the SDK people to test, to try out with their own networks. We can either do it internally or we can do it externally with the customers. And that would make it available, as we hope, to as large of an audience as possible.
Thank you. You can try. And our last speaker is Antoine Gauthier from QuantPy.
Hi. You know, we classified a lot of people into the hardware side and the software side. Might be today I'm even kind of in that third category. I suspect our software engineers, they would say no, but you're more on the theoretical side. But and to be fairly honest, I'm relatively new to tinyML. But I'm so happy to be here, and I will tell you why. Because I think what we have been working on in the past years actually is very, very much connected to a lot of aspects of tinyML and the challenge there. And what are we doing? So I will tell you in a second, but you know, I said I'm more on the algorithmic computational complexity side. This is what I'm really fascinated about. And when I saw the conference, wow, AI for good. Wow. It's been years that I try to understand what does that mean? Good. What is that? As a side note, I'm a mathematician by training. So, you know, I like to understand what I'm doing. That's very important. And this connects also to what Eden very nicely said this morning. Eden said she wants to sleep at night. She wants to make sure that she's working for a better world. Kind of. Yes, me too. And this will come in the next slide. But on top of that, to sleep at night, I need to make sure that what we deliver to our customers, I can rely on this information and I understand. And I can tell them, look, take care, please. You cannot use it everywhere, and so on and so forth. So, who is going to? Well, we are actually, I suspect, a relatively small startup. But it's been a couple of years. And in 2020, we really, you know, we have set ourselves the following relatively bold vision, I would say, is to enable society for a safe and self-determined coexistence with intelligence. So essentially, we're really working on the field of trustworthy/responsible AI, right? That's what we're working on. And what I will speak mostly about today, because this is really important to me, is the enable. And we'll see in a second. But why enabling? Actually, I can say it now. Is you know what I've learned, and I actually my father was working all the time in sustainable development, right, and so on. And what I've learned through traveling and this kind of interaction is it's hard to say. It's for me, it's hard to define for the others what is good. I prefer to give you the tools, the parameters, what you think is good, and then to see if in this sense you think it's reliable, trustworthy. That's why, you know what I'm most proud of here are 11 nationalities and all 14 languages for this set of a company. It's fantastic. Diversity is fundamental, I believe. Good. Let's go to a bit more interesting aspects. I made sure to have a presentation which may feel, if you want, a bit high level. But if you want, each sentence you will see here is an open door to come to me, sit together, take a piece of paper if you wish, and we can speak about math behind. You know, I will start with a meme that I saw on Facebook, right? Which for me describes so much things. We have this, you likely already saw it. I mean, it's turning everywhere around currently. And I think it's used to differentiate, to illustrate the difference between equality and equity. But that's not the point I want to make here. The point I want to make here is, you know, what's the most fair between the left side and the right side? You know, on the left side, there is this person who cannot see the game. But everybody has a box. If they want to make fire or whatever, very important. On the right side, well, they can all see it, but the tall person doesn't have a box. So in principle, here I would say, well, you know, which one is fair depends on what's important to you. What is the good? What does that mean for you? And once you know that, and start to understand, okay, what is fair and so on. But there is one thing which we did, if you agreed with me right now. If you don't at all, please raise your hand right now. I will memorize and we'll continue discussion after the talk. But no, what I want to say here is, you know, I think in both argumentation I gave for the left and the right, fundamentally we did the same approach. We counted, we looked, okay, two each have a bond. Yes, good. Everybody gets the same thing, which might be important, which we consider as important. And if you just vary what is important from the left to the right, you get which one is fair, either the left or the right, having a box or watching the game. And there's the everybody, which is also fair. And actually, what is hidden behind this sentence, well, you can formulate it as a math equation. I'm a big fan of probability theory, right? I'm happy to discuss later why. But you know, essentially, we can model these two situations under one hood with mathematics. And that's the beauty in the story, I think. And these are, I know, sorry if it may seem trivial, but I think the concept underlying here, I will try to give you a hint so you can model a lot of the trustworthiness metrics we understand nowadays in bias, fairness, explainability, robustness, and so on and so forth. And another comment I would like to do is, you know, if you just look at this equation, just look at the colors, right? The orange and the blue. Well, if you go on Wikipedia to look fairness metric in machine learning, you have a list like that of metrics. Vary the orange, vary the blue, you'll get them. So that's the part which is important to understand. Good. And what is another advantage of thinking at it in this way? Well, transferable. You can transfer these things. We are not speaking, I mean, we are not, so by the way, just to make things clear, at Quantify, we are not working on Facebook memes. We are working on real systems that we try to assess. And I would like to share a couple of small anecdotes with you, which I believe are also interesting. One thing is, you know, we were assessing the fairness with respect to gender of an autonomous driving system, right? But actually, it's just a small, it's a system which recognizes people, right? And what's super interesting, and I was super happy to see that recognizing people whether is not much influenced by their gender. What a catastrophe if from tomorrow on, you know, the self-driving cars use more often males or females. That would be crazy. On the less good news, I was assessing a question answering system deployed in a huge company, thousands of employees, actually working in the also sustainable development field. And they have this kind of you know, internal GPT, right, where you can ask, look, what should I do about company, like, you know, these processes, like, where can I, and when you want to apply for holidays, etc., what should you do? And I was, the first second I was a bit playing with it, and it's important because it's an international company. And I was asking, okay, look, I want to fill in, so I want to go on holiday, what should I do? And if you ask the question in German, great answer. If you ask it in French, wrong answer. And you know, we're speaking about education, and that's why I love also, so you know, exactly, AI for education, right? If you start to have some biases and you deploy that at scale, the impact is crazy and hopefully not too bad for our future, for our children. And then another example that I found very nice, and we saw many examples also of tinyML applications in this direction, is disease detection, right? And there are, well, you know, we face very different types of problems, and I will come to it in a second. But notice that to look at fairness or bias understandings of this thing, you need to specify two things: what you understand by everybody and what is important. Just that. But that brings you some trade-offs. And what are the fundamental I think, and here I share some experience over the past years. You have a trade-off, first of all, a trade-off between complexity and simplicity. I want to define that. Why? Let's take the first example I mentioned, right? You have this system for autonomous driving, you have data, good. You can measure when it's working, when not. But it's not written on the picture if it's a male or a female. You have to extract this information from the picture. You do that with another black box, which will induce errors in your measurements. You have to be careful with that, right? Because assessing a black box with another black box, yeah. If I want to sleep at night, because I want to deliver trustable information, I think it's very important to take these kind of things into consideration. Similarly, what is important? Sometimes, for text-to-text applications, a loss function, yeah, okay, sorry, I will rush, but that's why I have 5 slides. I went in the tiny spirits. Okay, but sorry, I will speed up. You have this kind of fundamental, yeah, you have to be careful because this is where you will lose reliability of the information. And then there is another trade-off, which is, again, you see, that's why when I was starting, I said, yeah, look, I'm also a bit more on the theoretical side, but the problem I faced in the past year was not like, okay, there is the compute power of ML and then of tinyML, but we were thinking even like, okay, what if we would have infinite quantum computer? And then what our customers are willing to invest in assessing these things, right? To be honest, it's more there. But to provide the possibility to control the complexity of the algorithm, we have to think a little bit about these things. And here, one big problem in bias is, you can use one characteristics, but then combination of characteristics, 2, 3. We looked at the size of people there, but what about looking at the color of their pants? And actually that's much less clear if it's fair or not. We don't have enough data. Essentially, what I want to say is if we think at it in this way, the computational cost of bias and fairness metrics is fundamentally governed by the number of data points, okay, with the complexity of the descriptors, right? The information you want to extract and the metrics. And that's the nice part, I think, because you can control, you have full control in the end of the day on the fairness metric you want to evaluate, right? And you know where is the trade-off, right? Extracting this small information, I don't know, size, right? This will upper bound the rest. But then it means if with lightweight algorithm, sure, then lightweight will run in low power environment. I would like to share 2 things that we have worked quite a lot on to try to address these kind of issues, right? The first thing, what I would really, when you do AI, this is super important. The confidence interval everywhere where you can, because there are so many situations where you just don't know it because you do that at scale. There's 1 or 2 data points, right, of a subgroup, I don't know, tall people with long hair, etc., etc., etc. And then you feel like, oh, we are not fair. But actually, it's not true. That you're working with not true information. What is your this was another thing. Another thing, which I think would be very interesting potentially also for tinyML, and that's where I wanted to come today, is, what we are doing is, okay, we've seen before, right? If you want to look at all the combinations of all potential properties, etc., 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 to understand where your where your system is good or not, right? This is a computational nightmare. And I mean, if you really want to do it extensively, even with servers, you're dead. But there are techniques from data mining to address these kind of things, right? And then to derive rules, lightweight rules, to scope the usage of the system, and to potentially prevent harmful behaviors. I said we had these disease embedded systems to predict disease. Well, try to understand, maybe we did it. It's possible to scope, to say, hey, wait. These kind of patients, be careful. In this way, you make sure that, you protect your system. And this can be done extremely lightweight. In the end of the day, it's just the cost of evaluating the group. Too long to finish, but you can watch it if you want later, because we're out of time. But what I want to say is fundamentally what I just told you about controlling the complexity of measuring fairness. And what are the trade-offs behind? Well, if you model it properly, you can do the same when you analyze robustness and when you do explainability. It's the same fundamental concept. Just replace descriptors with motivation. If you have interest in more details there and so on, please come to me anytime. But I think in order to respect your lunch, our lunch, I will make you
Or one or two questions for Antoine? Maybe I have one.
Yeah.
Do you have toolboxes that can be used?
Yes, thank you. That's what I forgot to say. I realize it now. Yes, all of that. You see, at the very beginning, I tried to separate the objective part from the subjective part. The objective part, we have implemented it, automated it, and so on and so forth. We offer products, right? Toolboxes where really you just that's a core function. It will compute the whole trustworthiness analysis and even save evidences about it for the more governance part and map it to some regulations. Thank you. Again, if you're interested, please feel free to contact me.
Great. So we have a session starting at 10 past 12. It's 2 minutes. So I guess we can take just 5-minute break and
10 minutes, maybe take 10 minutes and we'll start the next session a bit late. Okay, but can we be back here by 20 past? Yes.
A problem because it's all yeah. Organized. I was going to sound it by saying, I'm saying anything enough about that is fine. Other people.
Very good. Then, so you're the next presenter. That's fantastic. And I'm very, very pleased to hear about that. I would just have you totally honest or something.
Yeah, it's more secrets.
We try to see if the man actually gets equity or this is equity.
Thank you.
I don't well, I
didn't know how to go to school with that track.
Yeah, I know.
No, that's good. It depends. It basically, you could consider that as a tinyML application. You need
super focused for you.
the true one.
Yeah, I know the way.
Because then if you think about it.
You know, I never thought about it.
Maybe it's
I've
never know. Yes, it has relevance to that thing, right? It's a bit
whatever. So he, I mean, it's so obvious, but
and so then you could say, okay, within the bounds of my controller, that I already have.
no, at the moment, AM is used.
So there you go. There are probably more power in the sense of.
Probably never had a coalition. I think even during a party meeting.
Maybe.
Has to be a coalition. I expect to get about 12%.
Yeah, exactly.
Which is good.
A big push.
So that's not good for the country. And it looks like I think I read 10 to 14. But now he looks like he's going to get the highest, not on the 50, but the highest.
One brief question. Yes, so I work on tiny drones, maybe you heard the question. Yeah, exactly as well. And I've heard, that's why I've heard a lot about
5-6 years ago, he had a new child.
So I was wondering in general, in terms of using.
But it's an example of.
MCU
standalone. In fact, what they do with the Crazy Fly is they keep the STM32 drone flight control.
Yeah.
Because the flight control software is already installed, so it's less hassle.
Yeah,
right?
yeah.
And then they keep us as really doing neural network acceleration, but there's actually nothing that stops you.
This IoT.
There's nothing that stops you.
Yeah.
Putting all the flight control on. I mean, there's a controller portion of the chip that is an MCU that runs for yourself.
Yeah.
So there's nothing that stops you porting to that.
Okay. So it's essentially.
It depends whether you think that's worth it.
Okay.
Right? From an energy, from a time and energy perspective.
That's it, right? Like I don't know about memory sharing, all this.
Yeah, memory can be a problem as well. It just makes you compartmentalize the problem.
Okay.
Yeah, it's difficult enough already.
Okay. Yeah. So it's
depends what you're trying to do. If you're doing research, I would say keep it separate because you want to get to a paper quiz.
Yeah, that's always what our professor says. So that's what we're aiming for. Okay, that's interesting. So you can basically buy this the GAP9, and how do you program it? So how do you
wanting to do it on the Crazy Fly?
So it would be on a different platform. It would be on the we build our own like a wing drone platform.
Oh, okay.
But it's more for indoor applications.
It's still low power.
It's low power, yeah. So specifically the most interesting part is instead as well as the low weight.
Low weight,
yeah. Low weight, and with that comes low power.
Yeah, so from a programming perspective, we have a full basically classic chain GCC, CMA chain.
Yes.
The neural network side is everything from our TensorFlow Lite, and we have our own neural network.
Just hearing, which is.
People here calling compilers. That's a big word.
Yeah.
We have a mixes. I mean, TF-Lite is definitely not compiler.
Yeah.
And we have a mix of compiler and handwritten kernels. We have about 3,000 kernels now handwritten.
Wow. Okay.
And then everything that's compiled is compiled.
Okay. Yeah.
And our chains have all of that. We can handle make quantization, we can handle quantization across flow.
Yeah. Kenny is really good. He's always been on. Kenny.
Yeah. Okay. Very good.
And often changes that, so you can from Python, you can take a model, you can transpose it, run it on our simulator with simulator.
Okay, perfect. So you can simulate the runtime already.
All of the runtime, all of the results back.
Yes.
You can memory layout, you can get all of the results, we do tensors the whole way through, so you can from a Python work.
Oh, okay. That's very useful. Yeah, so you can do it even test.
Exactly. Behind the scenes, you can go in and look, what you find is a C project.
Yeah. Okay. Okay. Interesting. And so that also use some of the tinyML in the background, or it's all your house written?
I don't know. tinyML doesn't make
optimize. No. Because it does the optimization, right?
The organization doesn't do any engineering.
Yes.
So no.
Yeah. This is more about the communication.
No, I mean someone was talking about co-design. I'm all for co-design hardware and we do co-design. So
Yeah.
all of our tools are written by us because we design the hardware and the tools at the same time.
Okay.
And in fact, the simulation tools will be used to do that.
Okay. Yeah.
Because when we do new hardware, the first thing we'll do is actually write simulation of the new hardware and then we'll put it into the chip, so to speak, and then try it with our tools and see does this work well with the tools in a real problem rather than some kind of RTL simulation problem, which generally is a very small thing.
Do you have this like publicly available on a GitHub?
So that we've just started releasing the Gap9 SDK without the simulator.
Okay.
And in public. You have to go through a kind of hurdle to get to it, but you can get to it. With the simulator, you have to sign an NDA with us because the simulator actually has low-level details of some of the simulation in it.
Yeah, because you get access to the code base, I assume.
Well,
right? And
you don't see all of it.
Yeah.
Some of it's compiled, but it gives you enough that you start to get a sense of hardware architecture, and we don't really want to.
Okay.
Release that outside.
Okay. Okay. So great to be in touch because. Yeah, I think
perfect. We do a card.
Yeah,
you can go to our website. There's stuff on there. I must admit, from a research place perspective, we try to help. But within limits, right?
I understand, right? It can be very time consuming, right?
Customers are kind of a bit more important.
Of course, yeah.
But if you've got an interesting project, then definitely pass it by us because maybe it has relevance to us. I must admit, drones. Not sure.
Yeah, in our case, it's more about exactly deploying. I said like reinforcement learning and more on the control side of things.
Reinforcement learning could be an interesting topic.
Yeah.
We've already got people doing on-device learning.
Yes.
But not based on reinforcement.
Okay.
But there's some people in Love and
am
I right? What's the name? Never mind. Stops with an H. Anyway, there's a professor there. Professor there who's very into tinyML and there's one on the board as well. Actually.
Yeah. All right. It could be very interesting. Yeah, drones look for the lightest, smallest solutions. A lot of chances. Right. Thank you.
What chair? Yeah, exactly. What I saw really cool a few years ago, I actually interviewed this company. It's called National Instrument. They have an office. Okay, I would do that now. So I interviewed there, and they had these robots, which were designed very simple. Like all lines, pick up something.
I know. I mean,
and they designed like a
okay. Then I will try to
language where kids can go and like arrange blocks in a way in which they program the robot to go and do things. So now
you are
what I'm
part of
trying to do
the
is convince
whole
them
thing
that I'm working with the brain and teach them to engage national instruments to see if they can give us these robots to
bring it out today to be
I was at university.
and there are cases where even with a server, whatever, I just had to come from a different direction. There are so many data, so huge matrix, whatever, that solving an linear system is so big. Then what do you do? Even though you have your server, and these are the kind of mindset I find super cool because actually I think it's very close.
I'm gonna say.
One scale farther.
How long does she have? Seems like your lunch will be shorter.
I mean, yeah.
What time is the lunch break?
So the lunch is supposed to be at, from what we scheduled on us, it's supposed to be at 12:30.
How?
No, at 13:30.
1:30?
This is.
The place will close at 2, I think, so.
I'm gonna set a timer. I might just have to whistle stop.
I can do that. What do you mean? 15 minutes, got the 5-minute countdown at the end and good, I've got a
I'll
job.
set my time.
Okay.
one that some kids in Romania we went was up in their high school, and I was surprised that they.
15 minutes
built,
and
like,
30 minutes to start.
plants
Give
once
you
per
a 5 minutes
system would have like a field sensor. Detect that, oh, the plant's not happy, it doesn't have enough water, start
Yes,
putting a
I
bit of
will.
water in there.
I'll go and
That's
explore
one way
that.
to do it.
He's actually getting excited by that.
Exactly.
You just do something on the board.
Live stream. What's your background?
Go back.
It was scheduled to start at 12:10, but we've moved it back slightly to 12:20, so it's starting in the next few minutes.
Not yet ready, but happy to speak about it, because I mean, we are also a spin-off of this.
It's ended one for yes. These ones come in and out. They've got messages.
The Helmholtz Research Center.
Thank you so much.
How you like her?
Very much. It's been like I bought it like I recently came back from Japan, and while living there, the problem was that I love writing codes. I love having like my own notepad and like stuff like that. The problem was anything that I buy is something I then have to transfer back to Switzerland. Back. So this was like a very practical.
Sure, of course.
No,
Yeah.
version.
How does it work with yes? I have a remarkable, but not that.
We're not dying from the heat.
Anything but the
It's okay, it's not too hot.
I can speak one still.
Yes, we are.
So I'm gonna try and start back a little bit, not too late. So thanks for coming in. Director of Sustainability and Social Impact from ARM. Okay, so Fran is Director of Sustainability and Social Impact from ARM, and she was also voted in this year one of the most brilliant women in AI ethics with 100. So very privileged to have her here today and to talk to us. So just to let you know, we're going to change. So she's going to start the session, and then we'll move on with Mathieu Lemay, who will talk, and then after it will be Marco, and finally it will be Gabrielle. So there's a slight change in the program, just so that you're aware in terms of the order. So I let you go.
Thank you so much. And I'm taking a seat because I have a passenger, so I've got a great excuse. And what do we have on here? Yes, so I'm Fran Baker. I'm Director of Social Impact and Innovation at ARM, which is a semiconductor design and software platform company. I've had that role for the last 7 years. It's iterated over time. And I came to ARM from the international development sector. So I'll be talking today specifically about the for good aspect of tinyML for good. For the last few years, I've been privileged to be in the inaugural cohort of the AI Ethics and Society Masters Programme at Cambridge University. And I also sit on the tinyML for Good working group. So my world revolves around thinking about the impact of technologies, actually. And my title, Small is Beautiful, is twofold. One from the E.F. Schumacher book, which challenges the notions of quantity and quality. And secondly, more generally, that small things can be just as significant as large, complex, difficult things. Quality is not necessarily linked to size. And in this talk, I want to talk about that in relation to sustainability challenges facing society, because in my work, I care about what technologies enable, which is why I think I'm passionate about making space for tiny in the context of sustainability and impact. And I know I'm in good company being somewhere like AI for Good. So it's easy to see why scale and large scale solutions are gaining the most attention, I think, whether that's through their size technically or through the scale of their potential positive impact. We're living in volatile, uncertain, complex, ambiguous times. There's the climate crisis that we're trying to address. There's growing inequalities. And frankly, the need to decarbonise our economies is in conflict with the processing needs and expectations of the world. So we're seeing ecological crises, changing demographics, inequalities, polarization, all these massive issues that are affecting people globally. And at the same time, we're experiencing enhanced intelligence and pervasive technologies and disruptive technologies, the rise of IoT. But the problem is, in my view, I should always caveat, in my view, what can be done technically is not necessarily what's socially or environmentally desirable. So our sustainability agendas and our digitalization agendas aren't necessarily aligned. And I think a lot of people are looking to kind of these big saviors for technology, where one magical solution comes from one amazing company to solve the climate crisis. And we're kind of betting on these big wins and effectively betting on our future. So I want to talk today about how some of the answers can be found in examples of people addressing challenges on a smaller scale with smaller technologies. So let me show you now why I think both sides of this spectrum are important. One of the programs that I'm involved with through my role at ARM is a program in Malawi. So since 2015, we've been working with UNICEF and their Office of Innovation, combining our expertise and to use technologies to support young people globally. And sometime around 2018, I happened to be on a call with somebody from UNICEF's Malawi office. And I was learning all about the different programs that they were building or wanting to build and the digital expertise that existed within the region. And honestly, I was completely blown away by what I was learning and hearing from this community, and I wanted to collaborate with them. So in 2019, I visited Malawi with a team of engineers to see how we might use our business capabilities to use them towards inclusive innovation. And it was a really, really powerful experience, learning from the technical expertise in the region, understanding the very specific challenges relevant to a Malawian context. And through this co-creation trip, we landed on a number of interventions that were both needed by the Malawian team and where we as ARM were able to proactively contribute. So whether that was through technical, financial, or human capital. And for those of you that don't know, Malawi is a landlocked country in southeastern Africa. 80% of the population live rurally. It's known as the warm heart of Africa because of the kindness of its people. And it's particularly prone to adverse climate hazards such as flooding and landslides. And the thing that I could talk to you about many different partnership programs within this Malawi context. We've done things like sensor-based real-time monitoring for water quality in rural parts of the country. We've done predictive flood modelling and landslide modelling with the Malawian government. But the specific example I want to share is the African Data and Drone Academy. So the African Data and Drone Academy, ADDA, was established and designed to teach young Malawians how to design, build and pilot drones. This addresses a multitude of different challenges related to drone technology and accessibility in the area, whether that's from, say, component part import costs or enabling 21st century skills of the younger population there and having this kind of end-to-end knowledge for the students. But importantly, the programme was designed to upskill students on drones and data for development and humanitarian purposes, problems relevant to the African and specifically Malawian context. And many of the students have gone on to use their drone skills to solve those problems. So, for example, there's some students that have gone on to work and delivering vaccines to rural parts of the country or combating cholera with health NGOs. Another great example, another great outcome of that programme is that the students are actually helping the government improve their emergency preparedness by doing a lower level of land surveying using drones that kind of fills the gap between massive satellite data that's at a much higher level to the local population data that they actually need. So they're using their skills to inform the authorities in predicting in disaster preparedness in a really relevant way. And so I hope from this example, you can see that there's a role for technologies in different contexts, particularly in resource constrained environments. And whilst recognising that drones are at the higher end of the tiny spectrum. But I'm pleased to say that when I returned to Malawi last year in 2023 to see how our work was developing, there were 3,475 enrollees on this programme, 1,331 graduates, and 60% of them were women. So what I'm trying to show through this example is that this programme's had an extraordinary effect on the lives of those involved in the programme itself, but also the technological skills that they're bringing to the region, to their country. And we often think about AI in terms of the ability to scale and scalable solutions, hyperscalers, global reach, applications that are absolutely enormous, and think about billions of parameters or data centers that take up thousands of meters and hundreds of engineering resources. This is AI that we think of as for everybody, but not everybody can necessarily access it or use it or benefit from it. It's faceless, you know? And yes, those technologies are going to be critical for addressing some of the global sustainability issues that we're facing. I am not disputing that. But it's not going to be that one technology or that one organisation that saves the world. So I don't believe that impact has to be big from the technical capability perspective or in terms of the numbers reached. I don't think reach is an accurate proxy for impact. We often hear about these super sophisticated systems in the press, but they're not always ready and they're not always relevant to all contexts. So I think the potential for Edge AI and tinyML specifically is that bringing intelligence to objects that are all around us means that tinyML finds its natural home wherever a power supply from the mains is impossible or difficult to come by, and an application has to operate with a battery for as long as possible. So I think this means that tinyML is beneficial in places where, number one, internet access isn't always possible. So, for example, in remote regions or places with intermittent, unreliable or expensive connectivity, which we can see quite often in global south countries. Number two, where there's latency implications, for example, where you're sending and receiving data to the cloud and it's not instant. Three, where power consumption is an issue. So, for example, sending data to and from the cloud is not power efficient. And four, where there's a security concern. So, for example, in spaces where it's necessary to avoid communicating sensitive information. So you can imagine that in kind of health or humanitarian settings. And I think another beautiful benefit is that everyone can have access to the most powerful technologies that are changing the world. So tinyML gives power to the people and allows people to solve problems in a democratic way. I've got a note here from somebody mentioning yesterday that power needs to be distributed equally. That was from Doreen Bogdan-Martin, and that it's ethically precarious to have power concentrated in too few hands. In my view, tinyML is addressing that problem. And it means that millions of individuals, smaller organisations, communities can be addressing problems that matter to them, not waiting for some big solution to helicopter in and address all the problems, but actually taking ownership of the issues and having this life-changing impact that's possible both through smaller models and smaller scale. And this can apply in so many contexts relevant to sustainability. I realise I didn't skip on, but there we go. Big impact is actually tiny impact. This can apply in so many contexts relevant to sustainability and to impact, whether it's low cost, easily implementable classification and identification systems for species. Lots of people are using this in wildlife conservation spaces, for example, whether it's deploying technologies for humanitarian purposes or in education context. So Arduino, Microbit and Raspberry Pi in order there. And I know there's some people that are tinyML experts, some people that are brand new to this. These are all examples of how kids can learn physics and maths and programming and see the actions of what they build in the physical world, in the real environment. So education applications with tinyML mean that creations can go beyond computer boundaries and make this real world impact. And that's possible because microcontrollers are widely accessible, they're low cost, and they exist in this very engaged open source community. And so tinyML is about bringing intelligence to objects all around us. tinyML's this set of technologies in machine learning and embedded systems, making smart applications on low power devices. And for me, these three key benefits it brings are in terms of power consumption, data privacy, and cost. To me, it's not difficult to see how those benefits can play a significant role in the space of sustainability and tinyML for the SDGs. But when the world needs to go on an energy diet, we know we need to address power consumption. When there's pressing healthcare and humanitarian situations, we know we need to address data privacy. And when we're considering operations in low resource environments, we know we need to address cost reduction. And so for humanity to benefit from the advances in technology, it's my belief that we need to be putting them to work for what's needed, to build resilient systems, to build inclusive societies, to decarbonise our futures. And quite often, the people exposed to these challenges on a daily basis are the people best placed to come up with solutions to address them. And for people and communities to benefit from transformative technologies, those technologies need to be accessible. And for me, tinyML gives the power to the people, and it's an enabler for those types of thriving communities. So it's not waiting for big tech innovations and advancements to trickle down gradually over the years. I think we need to think about size and scale differently to recognise what scale means in different contexts. Like I talked about ADDA, they're small numbers if you compare them to global reach, but in that context, they're absolutely transformative. And I believe that giving people, regardless of their expertise, the power to address the sustainability challenges that they are facing with technology that exists today in an affordable way, and they're able to bring projects to life for just a few dollars is just so transformative. So in a summary to my whistle-stop tour of tinyML for good, I believe that tinyML is part of the answer to AI everywhere, and that small is beautiful. Thank you very much.
Actually, we programmed that the questions all come at the end of the session, if that's okay, because for timing and also for lunch and also for lunch. Just thanks very much, Fran, and I think it's a really important point, you know, particularly at the end where you mentioned the fact that this empowers the people, and nobody but the people suffering the problem understand the problem so well. So by giving them the chance to make the solution and really make a huge impact, which is what we're looking for. So thank you. So next up is Mathieu Lemay. Yeah, okay.
Just switch it.
Yeah, okay, so he's going to be talking about digital health, and he's a group leader at CSEM, who's running the signal processing and AI group there, and he's probably over 20, I won't say 30 yet, 20 years experience in the fields.
Depends how you see.
And also, I think he will be telling us not just on the wellness, but actually on the medical side of it as well. So welcome, Mathieu.
Thanks for the introduction, Andrea. Yes, I'll do my best to keep a balance between being too much technical and not enough, depending on your background. I know that digital health, I'm lucky to have a topic that is of general interest, so I'll try to reach all of you as much as I can without going into technical details. But first thing first, a couple of words. I don't want to make a pitch out of the CSEM, but just to let you know what the CSEM is all about. It's a public-private, non-for-profit Swiss industry. We build technology bricks, and our goal is to transfer our technology bricks to the industry. So the team that we have, we address many domains. The one that I present today is the medtech or the digital health one. But we address many things: energy, green tech, additive manufacturing, image processing, a lot of sensor development, MEMS, and so on. At the CSEM, we are about a little bit more than, now I think it's a little bit more than 600 employees, most of them former PhDs in their own specific domain. So this represents the CSEM. Again, our goal is really we can see us as a bridge between universities and the industry. So we really do applied research Our goal is really to transfer what we do. It's not just to do publications and to work on challenging solutions. It's our challenging problems. It's really to bring those technologies onto the market. So this is for the CSM. Okay, so now the digital health. I think it's about more or less 2 decades ago, it has started with the smartphone. People are started to feel a need to quantify themselves. How do I behave? Do I work enough? Do I eat well? And this has started. This is correlated with the smartphone, the application of the smartphone. And then the smartwatches has bring another level. So we are not only able to track the motion or the behavior of the subject, we are now able to obtain really interesting data from smartwatches. So this is can be seen as the beginning of the digital health from a subject perspective. There's something also in parallel to that, is the transfer from the knowledge and the control of the medical staff through the subject or the patient itself. People want to more and more to own their data, to understand their health conditions, and to play a role into the diagnosis and the treatment that they will follow, basically. You can see the digital health in 4 segments. The two in yellow represent those related more to the management and the public awareness of health issues. So you have the trend health, basically this is what I was referring to quantify themselves using wearables to social media, sport, really to improve your fitness, your wellness level. On the other side, you have the e-health, which is not really addressed by the CSM here so far. It's really to digitalize basically the information of the patient, to instead of writing everything on paper and printing and the old-fashioned way, it's really to digitalize the information, to facilitate the tracking between different departments, having the aim to really centralize everything regarding the patient and not the department at the hospital. And then on the bottom part, it's the two sides of digital health that really address the technical aspects. First, the tech health, which is related to sensors, biomarkers, robotics, genomics. Really, the innovation there that we've seen over the last 2 decades are amazing. And then in complementary to the sensor, you have the data health part, data scientists, all the tools, the signal processing, the data analytics, the big data approaches, the IoT ecosystem to collect more and more data. This is really fed by the 3 other segments, and this is really, AI is all about. Sorry. Just to give you an idea about the importance of AI, ML on the medtech or digital health domain. These are 2 graphs that shows the evolution of the interest over the last 10, 15 years. On the left, you have the number of patents associated to AI in the medtech domain over the last from 2010 to 2020. You see, this is not a trend, this is a brilliant exponential. And you see more or less.
Good afternoon, lunch is served. Golden Leader Pass holders can go to room 14 inside the Leaders Lounge on the 2nd floor for their buffet lunch. All other pass holders can purchase lunch at the ground floor cafe or the 1st floor cafeteria. Bon appetit!
Or you can still stay. And on the right side, it's more or less the same behavior. It's the growth in percentage with respect to no, this is not patent. Yeah, this is also patents with respect to general patents and patents related to AI in medtech. So you see really strong exponential in terms of innovation. If you look at what it means on the market, on real products, this is, I like this picture because it shows the distribution between different domains to medical domains. As you know, AI, ML, most of the tools are really well designed, dedicated for image processing. So there's no surprise to see radiology as the first or dominant medical domain here. Unfortunately for you, I will not focus on image processing. My 2 colleagues would have been better suited to do so. I will focus more on time series application, simpler. but this is give you an idea. And we see that GDG has really stepped, was the first step, but all the other domains are getting more and more interested into AI ML solutions. A few words about what we do at the CICM in the digital health, please. Three technology pillars. We look at movement analysis, basically 3D accelerometer or inertial motion unit. Sometimes we use also a gyroscope barometer to develop human tracker, gait analysis, movement analysis parameters. The second technology field is related to, and movement analysis for us, it's really, we address more or less only the algorithm aspect, because the sensor part is really the state of the art that you see on the market is really enough for the precision that we need. But the second and third technology pillars address really the system point of view. So we have a technology or bunch a technology portfolio that use PPG signal or photoplethysmography signal. Basically, this is a technology that is used to estimate the amount of oxygen that you have in the blood. And it's also more or less the same technology that your smartwatch is using to track your heart rate on a daily basis. So we were the first one basically to use this technology to track the heart rate with a smartwatch. And over the last, we started in 2001, and over the years we have developed solutions to track other parameters, HRV, sleep, SpO2 or oxygen, amount of oxygen saturation in the blood, and also blood pressure and cardiac arrhythmia. So we see there's a trend from fitness, wellness parameters to really medical applications. The third technology pillar is what we call the EXG. It's also another patent portfolio that allows us to design different form factors to monitor basically the electrical activity of specific organs of the body. EXG, the heart, EEG, the brain, EMG to monitor the activity of the muscles, and so on. So we have access to these three, let's say, platforms, and we have also the skills to analyze the data with data scientists. And on the top of that, we are certified 13485. So we have the quality management system to really develop medical devices. This is really important. So now the idea was to use two extreme examples, one on the consumer or quantify yourself, and one on really medical application to see the methodology that we do our best to follow and give you an idea about also the potential of tinyML approaches. So the first one, human activity tracker. So we have plenty of products on the market that track your activity. If you do it properly, you can not only detect only steps, but you can classify the activity. This is the approach that we decided to design. We first detect the activity, the physical activity of the owner, because it's necessarily a patient. Then, based on the classification of the activity, we develop sub-parameters that are of interest. For example, if you're walking, then the steps, energy expenditure, speed, distance, and so on. You can do the same thing with swim. If you detect the swim, then you can adapt your models to detect energy expenditure when you're doing swim activities, and so on and so forth. Sleep is also an interesting pattern. It's between medical and fitness wellness applications, but it's more and more used and available with your own wearables. So this is where more or less the market is. Some of you mentioned that during the hardware session. It's always important to keep in mind what is the context or the conditions of your challenge. So here I'm focusing on algorithms, of course, but it's the same for hardware when you design a hardware. So regarding human activity tracker, since it's a consumer product, a consumer application, let's say, basically in terms of accuracy, it's at least to challenge, if you want to have a successful solution, is to challenge the leader on the market. Here, I didn't put Garmin, Apple Watch, or Fitbit devices, because for me, they are the leader in terms of market for consumers, but they are not yet at the level of being used in clinical trials. Actigraph is the leader if you want to, example, validate drugs. You wear an Actigraph at your hip or at your wrist, and then you validate that there's no impact on your mechanical behavior due to drugs. So they are really the reference for step counting. Then other parameters that need to keep in mind, it's to be as low as possible in terms of power consumption, because usually most of the use cases, they address 24/7 monitoring. Long term, you don't want to recharge your wearables every day or every week. So it's always a component that is important to keep in mind. And if you do a great job, you could even address to be multimodal and body location agnostic, basically, to have an algorithm that detect, example, the step, but not only using a wearable at the wrist, but also a wearable at the hip, at the ankle, at the head, at the ear, these kind of things. So this is what we have at the moment. This is, without going into details, this is the structure of our algorithm. But basically, at the end of the day, we have 3 axes here, X, Y, Z. This is an example, I think, at the wrist, because this is the most common one, but you can do the same everywhere. And we extract specific feature out of these 3 accelerometers, these 3 3D accelerometers. Basically, we look at the cadence and the amplitude of the cadence and the pattern over time. And we are able to build, I was talking about probability, that Antoine, it's you that likes probability. So we build a model that defines basically the probability of being at rest or walking or running and so on. And this is the core of the technology. Once you know what you're doing, then you can adapt many other sub-models to be really specific on the parameter that you're tracking. Here, little projection into ultra low power, because the solution that we have at the moment for me is really low power, embedded C code. This is the footprint for you who are interested into this. And this is the really interesting part. I know that you guys are working on the hardware part. There's a new family of initial modules branded by ST, where you have processing power directly in the unit. So, example, in our case, we haven't done it yet, but that's the plan. Basically, the newest one, you have a nice CPU directly in the sensor. So we could compile our algorithm and run it directly on the sensor. So without going into details, it means that if you have a wearable, then you don't need to wake up the system to process the data. You just process the data directly on the sensor. So it has a huge impact on the power consumption of your wearable. Okay. Another extreme application is the blood pressure monitoring. I don't know if you're aware of that, but in Occidental countries, 1/3 of the adults suffer from hypertension, and half of this 1/3 percentage, they are not aware of it. But it's really a huge problem. How you diagnose hypertension? Basically, you wear an ambulatory blood pressure automatic cuff over 24 hours or 72 hours. That pumps and measure your blood pressure every 30 minutes. So it's not convenient, it's a little bit cumbersome, and that's the only way to diagnose blood pressure or hypertension at the moment. There's a lot of teams or product that wants to improve this solution. We have worked with some of them, and the idea, one of the techniques used to improve the situation is to use PPG or optical signals to estimate the blood pressure. And this is where definitely, there's other solutions, but this is definitely where the market is going. So in opposition to the human tracker, human activity tracking application, in this case, the first requirement is to be compliant with the standards to design medical devices. The second requirement is realigned with the standards. So you need to be aware about FDA, CE marking, ISO standards to really address them carefully when you start the design of the solution, which is a little bit different from consumer or let's say less important parameters. And the rest, body location analysis, be robust against PPG quality robustness. Example, if you want to build an algorithm that is able to run on different systems, then you need to have mechanisms to control the quality of the signal that you receive, because it's not always homogeneous at all. Let's do some physiological procedure. So the technology that we are using, let's say we have the heart here. When the heart, sorry, it was supposed to be an animation. Anyway, it doesn't matter. When the heart is pumping, you had let's say the blood flow that propagates over the arterial tree. So it creates a first miniature of pulse that you can see here. And then you have also reflection over this arterial tree. The first one being the arto-iliac bifurcation. So it creates the second bump, which more or less looks like a camel-shaped pulse here. And out of this specific pulses, we are able to extract well-documented features, and we build our model based on these features. So where we stand now, we have this solution. So as you can imagine, the RAM here is really too high to be treated as ultra low power. So now we are challenging our model with data-driven solutions. We want to get rid of the calibration aspect and basically using our solutions, eventually try to integrate everything into a single chip. So here, just the keywords regarding the presentation. I won't go into details, but basically, for those of you who are working on algorithms, do not fall in love with your architecture, because this is something that I see quite often. When you have a tool, it's Churchill was saying, when you have a hammer, you see nails everywhere. The architecture and then architecture is really the same for me. And then I think I've tried to convince you, but it's really the trend regarding data-driven personalized healthcare is huge. There's a topic that I didn't address here properly. It's everything regarding decision support system solution. There's a huge market there. So there's a lot of possible innovation to do there. So yeah, if you're in the field or interested in the field, come and visit me.
So as we said, we're gonna have questions at the end. So now I just introduce Marco Zanaro, who's from the Abdul Salam International Center of Theoretical Physics from Trieste. But really, he's going to talk a lot about ICT for development and IoT for development.
Right.
Yeah.
Thank you very much. So ICTP is a UNESCO organization, and with a very specific focus, which is supporting research in developing countries. So as such, we have organized many training activities in Internet of Things. And, that's very interesting. But number one issue has always been communication. So the phenomena we're interested in, water quality, water level, weather station, they usually happen in places where there is no connectivity. So when I heard about tinyML in 2021, I thought that's a great solution for our colleagues from the Global South. So together with some colleagues, we set up a network and we said, we should support this community of researchers by, providing the best possible training material, by supporting them with equipment and with, enabling like new solutions for the unique challenges in developing countries, which as you will see are quite specific. So we organize many workshops and seminars on tinyML so people can learn about the technology. We have an online forum now with over 1,000 researchers from all over the place. And we have open exchange of student projects. So very often you were mentioning the sign language. You will see later there's people working on that all over the place. So why don't they work together? They share the data set and they come up with, a common solution. We have a website, sorry for the missing G there. So tinymledu.org. So you're asking about where you can learn about tinyML. That's a great place. All our, workshops, they're all published there. You see, you get the slides, the videos, the training material, you can reuse it openly. So there's a lot of material where you can learn about tinyML. So in 2021, remember it was COVID time. So at that time, we got some funding to support universities with this training kit, which is the one that is used in the edX course by Professor BJ Reddy from Harvard. So if you want to learn about tinyML, you have some time, you can follow that course and they use this kit. So we got some funding to distribute this kit, and we distributed to about 50 universities, the Global South. Each of them received 10 of these kits, so they can organize, lectures for the students. So that was the first step. And then we started organizing workshops. So again, 2021, We had 200 participants from 48 different countries. We focused on the scientific use of tinyML, because then again, we're a scientific institution, so we're kind of interested not on the consumer side, but more on, gathering scientific data in these countries. So, very well attended. It was like 1 week long. Then in 2022, we said, why don't we organize like regional workshop? With the idea that if you're, from Latin America, you might have issues specific to Latin America. So we had 3 workshops for, these 3 different regions. And as you see, we have, hundreds of participants. And those were, again, online, and you will find all the material on the website. Last year, we had another one and had 400 participants. So even, gathering even more interest. And again, we had the big players, Professor Aredi from Harvard, all, the academics working on tinyML are lecturing in our courses. And then 2024, I think people are kind of a bit, tired of online courses. So they started asking for, in-person events. So we had a couple. I missed Malaysia. The first one was in Malaysia, but we had one in Saudi Arabia at KAUST in Jeddah. And you see that some of the, applications are the kind of traditional tinyML ones. So keyword spotting. So people using that for video games, but we have also very local ones. So these people are using the camera on the tinyML device to find out the ripeness of date fruits. So date fruits are really, really, big part of the, culture and also the economy in Saudi Arabia. So, being able to detect if the fruit is ripe or not is kind of interesting. So very specific. Someone mentioned that people come up with specific application, and that's just one example. Then we had one workshop at UNU in Macau, UN University, people from all over Asia. And yeah, you see it here, that was just a couple of months ago. And interesting enough, in 5 days, people learn about tinyML. They learn about, the theory, about the practice, but they also come up with applications. So this was a group from Macau, and they came up with an interesting application that uses the camera to detect if you're in a difficult situation. So their idea was you can install this small device in a bar, and if someone feels, harassed, you can just raise their hands, and the system will detect the specific signs and send an alarm. Just to say that people come up with really interesting ideas and applications. So just a few weeks ago, we had even, one more workshop. This time it was on advanced topics, again, about 200 participants. Application people came up with in this network of 50 universities are super interesting. Just a few examples. Our colleague from Zimbabwe came up with an application to detect foot and mouth disease detection. So you have this, kind of $10 device with a camera, you stick it in the mouth of a cow, and you can detect if there's disease or not. Our colleagues from Rwanda came up with, someone mentioned respiratory diseases. Again, it was a time of COVID. Young student from Benin being able to detect disease in cotton plants, and that kind of raised the issue of data set that you mentioned in the opening. So very often there is no data set for this specific application. So he had to collect the data set and then come up with the model. Our colleagues from Argentina came up with an application to study animal behavior. So this is not a tiny device, but this tiny enabled device that they had access to with a huge power bank. So again, not in the direction of really tiny, but it's a really nice application. And with these kits, then people started teaching. So it's kind of a multiplying effect. That's our champion in the top left there, Solomon from Ethiopia. He organized 12 workshops all over the country using this kit, so training more and more people. Interesting enough, people also publish papers. So by having these devices, coming up with ideas, they could. So in the last 3 years, we have about 20 papers published in our network, which in my view is kind of a success. Just a few examples. So Irene from Rwanda, she's using tinyML for predictive maintenance in hospitals. Our colleagues from Moats from Sudan, and I also work on that paper, we classify mosquito wing beat sound using tinyML. So the idea is that you can find out what kind of mosquito you have in the field by measuring the wing beat. So using the audio capability. And then, people using that for coffee disease detection in Brazil, or atrial fibrillation was just mentioned. Again, doing this using low-cost devices. Output of all these activities is a book. which is completely open. In fact, it's edited by Vijay Reddy from Harvard University. Many members of the community contributed to the book. And it's not only open to read as a PDF, but the source is completely open. And the slides for each chapter are also available and open. So if you want to learn about tinyML, this is a great source. If you want to teach about tinyML, it's a great source. We, at a certain point, like in 2022, we found out that younger people, so students, were a bit intimidated by, this kind of more academic workshop. So we came up with this idea of a show and tell. So we have one per month, and that's a place where practitioners or, younger students can present their project. And then again, I think, okay, here we go. Gesture recognition. This was a group from Algeria, but then following that, there was a group from Texas doing exactly the same thing. So they, they're now in touch. They can work together and share the data set. But many of the examples are really interesting. This is an interesting one from Peru. They're using tinyML to detect anemia by the eye. So it's a big issue in Peru. I had no idea. And they came up with a really cool application where they have a 3D printed system. People they're facing, it picks up the eye image and it can detect if you have anemia or not. Again, we're talking about maybe $20 system, so it's extremely low cost. We presented all these activities to the UN, so we're in a UN conference now. So that was presented twice in New York. They have big event about science, technology, and innovation. So we presented that twice, and we had some policy recommendations. Finally, just a couple of weeks ago, we published a paper about tinyML for development, about how to scale this education in a developing world. So if you're interested in that, there's a QR code. There's a number of organizations that supported these activities. So Harvard would be one, Unife in Brazil, Barnard College, Columbia University, and then Egimpulse, Arduino, Seed Studio, and the tinyML Foundation. And just to finish, that's just some feedback from our participants in the last workshop just a couple of weeks ago. Thank you.
And just for the final talk in this session, so thank you for everyone for keeping on time. Actually, this is from Gabriel Caffi, who after 20 years working in Thales came back to Switzerland to head up a group on embedded processing and security. But he's here today because they won the challenge, the tinyML challenge, and he's going to talk about that. And so it's also a shout out. We'll have another session about it later on this afternoon, but also to say we're here today to look for NGO challenges. So please come to us. Please
Thank you,
go.
and thank you for the opportunity to speak about the smart weather station that we developed in CCM in the scope of I think it was the first tinyML challenge. The work was led by Yona Bessens, who's working in the team, and they won at the time the gold medal, first prize. So I brought some goodies. So how it looks like. So this is the object that we will be speaking about today. It's the first version of this smart weather station. You can see an illustration here. It's on the top roof of the CSEM, and I'm not going to go through it. Okay. So to start with, what was the motivation behind the development of this smart weather station? Is the idea was to develop a low cost platform that could allow to measure wind and rain without any moving parts, very low maintenance, and to minimize the cost for the installation as well. In order to, and the idea also is behind it is to have a dense deployment of these weather stations, contrary to more expensive ones with very precise locations. Here they have the flexibility to develop in smart cities or in remote locations with a very low cost. As you can see here, the existing solutions have have also issues on mechanical failures because they are based on mechanical parts, moving parts that require as well, it increases the cost for the Aurora project, which is the smart weather station here, offers wind and rain level classification, as I mentioned, maintenance free, and we have we insisted on working on real world conditions. As you can see here, we put it on the top roof of the CSEM, and we have also planned to deploy it in multiple locations of CSEM inside Switzerland in order to have a more robust data set here. It's also fully embedded machine learning. No, we do not have any. We use standard SOCs, so there are no specificities regarding in-memory execution or stuff like that. So it's really standard system on chips. So under the hood, so we have inside the weather station. As you can see here, we have environmental sensors, humidity, pressure, and temperature, atmospheric pressure, and we have also microphones in order to listen to them. And the engine, the ML engine, based on TensorFlow. Here more focused, more in detail. So you can see here a second installation we made also on the top roof, where we developed as well the pushed more the concept of sustainability by doing some tests with the solar panel so that the weather station be autonomous. And you can see we have a mechanical weather station. This is for the data gathering. We needed to have ground truth for this, so it was really to build all the data set that we needed here. And you can see here the summary of the overall architecture over I2C protocol. We have the pressures, the sensors, environmental sensors. We have also the microphones on I2S protocol. And we have stages of data acquisition on the device transmitted. On this deployment, I think we use Ethernet connectivity. On others, we use also Wi-Fi. That's in close to Basel. We have also an installation there, and that's transmitted over QTT servers. So here the idea was to build a large data set that we also that was offered to the participants of the next challenge, which is I think the winner will be announced today. And so we offered the acquired data set looks like this. So it's mainly the audio recordings are 1 second, duration is 1 second, precision 80 bits, and 16 kilohertz of sampling frequency. And you can see here in the data set we have on the structure. You can see that we have the ground truth here and the data from the BME, the Bosch sensor that provides the environmental conditions. The realistic data set that we generated contains really noisy environment. We have sounds that come from traffic, machinery, really very, even if it's in Switzerland, it's very calm. It's not very noisy, but still, I mean, we have a realistic one. So we collected data until August 23, since August 23, sorry, and we have this large database that we today the participant to the challenge. Okay, so the development process looks like what was presented this morning, very classical, tinyML and the tinyML framework, training, quantization, conversion. We generate the model and we integrate it into the tinyML boards. So here it was, the first version that we developed here was based on off-the-shelf components that we assembled. So we had some electromagnetic compatibility issues, hence the duct tape around the box, because we needed to isolate all the electromagnetic radiations, make sure that it doesn't have any issues there. But now we're working on our second version. But it's let's say it's a custom hardware with where we integrated as well our own real-time OS that has a very low footprint, very low power consumption. It's typically the kind of real-time OS that can run on smartwatches. Here we can see the footprint here for the kernel. It's less than 100 kilobytes, so it's really very compact stuff to make sure that we have the less footprint as possible. Here we can see some results. So here we see the results for for rain and wind for 2 classes each. We have very good results for rain detection, and for wind it's less accurate. So it's a work in progress today to make it to have a better results. But we obtained this result here. We also experimented with 3 classes. The idea is to have, we do not know yet what is the best trade-off yet in terms of class. Should we increase more or limit the number of classes and increase the accuracy? But we did some experimentation as well with 3 classes as well. You can have a live demo in the showers of the CSM. So you will see the roof and now the showers. Let's see here, try to simulate some rainy conditions in the shower. You can see that here the top was designed to resonate, to make sound, to amplify sound. So there's the titrate about class 1 pieces. Steps. Same for wind. Same here. Experimentation as well. You can see the results with 2 classes and 3 classes, same principle. Strong with women. You see here, yeah, how it switches. And here the wind stops. Future of Aurora. So here you see the new hardware that we designed last year. So it's still under testing, and we're under development, say, the firmware as well. And from the speech before, I heard the remark about connectivity. So it's one of the issues. So we tried this board. I would say it's a bit fancy. It's not supposed to be low cost, but we added many connectivity, LoRa, Wi-Fi, and we even had a slot for possibly for LTE, LTM needed. So it's really in testing process to see on the data collection process how we can enhance this part and to see what's working better. So it's want to enrich more our database and refine a bit more the inference, and to see, as I said earlier, refine the granularity for the classification, how many classes where we can stop or what's the most accurate. And the final item is working also on wind direction. So here, a part in acoustics would be implied. So it's we have research there to do on the acoustics part as well, through microphone array, other techniques. Yeah, and that's it. Thank you.
So I think we saw that really the impact is about local users and local education and getting the educational tools to the local users so that they can make a difference. We probably have time for one or two questions if the speakers want to come up. You want to come up so that you can answer questions? And then people were very good about keeping to time this time, so thank you very much. Are there any questions? No? Yes?
Yeah, so for the weather station, my question is, for detecting the wind, which kind of sensors did you rely on, like pressure and microphones, or?
So the approach is still the same. We do not want, we want to stick with the microphone. We have looked into ultrasound as well, but it's more expensive. So we have more expensive sensors, so we excluded them for the moment because of their cost. So we try to, we want to multiply the array microphones using 4 microphones now, and also working on the acoustics of the box, possibly to see how we can enhance this part and to get a more accurate information about the wind direction.
Yeah, thanks for all the presentation. I mean, I find it very cool, the idea of democratizing technology, but I was wondering what the stance, I guess, of the tinyML community was on surveillance and how do we enable democratization of technology without needing like some sensors that's can then be used.
I can answer that.
Yes,
So I mean, I think that the tinyML community, I mean, it's a foundation. So the idea is to keep the data in people's hands, and this using it locally is exactly designed to do this. Of course, you know, we also need to understand that, as we mentioned before as well, that there's a lot more data coming up which can be generated, which also removes a lot of the problems that you have on this. So that's one possibility. At the same time, data and data which is linked to particular applications, it has a value, and therefore you can't be naive about it either, in the sense that it is going to be chased by the companies. And but the tinyML community, what we try to do is bring in the companies and the end users to work together so that this is done responsibly. And I think that that's already been discussed at the beginning. Yeah. So that's the idea. It's by bringing them together as a community that we do this responsibly together. And the big companies are looking to do this as well. They reach out to tinyML to do this. Sorry.
Just want to add one small thing, which is about ethics. So there's, you know, lots of discussion about ethics of AI, but in tinyML, I think it has, you know, even higher, I mean, more importance, because now we have these devices that we're, you know, deploying in the field. And if something is wrong with them, if the system is biased, then you need to pick all of them and reprogram them and no. So I think kind of the ethical, in fact, in our workshops, we, you know, give a lot of attention on the ethical use of AI.
Yeah, actually, for the connectivity part, we were thinking about that part is that you may need to have a feature of model update over the air at some point on these devices, because they cannot stay operating on this with the same models. So we need to offer to have kind of holistic approach with. There's the communication cost, which could be a real issue, but there's also the to be taken into consideration to the design, or you can have you can offer high data rate or low data rate on your device, security as well, in order to have let's say with authentication, data encryption, and to make sure that these devices cannot be also hacked with, easily. Let's say because they are on the field, so they can be available to hackers. So the idea is to resist the first level of attacks, and plus all the possibility to do what they are designed to do at the end of the day. Yeah. But it's a holistic approach, and what we try to do here, and typically in this example, is to contribute to the community by making data available. I think data is the main, is the cornerstone for these designs.
But how do you actually plan on updating, and is big tech doing it better or differently? Because, for example, Google is demonstrating now there's also something for mapping flooding and predicting the weather. So are you offering kind of the same service maybe on a different application, or and where is the drawback maybe of tinyML versus huge tech?
For me, it's two different topics. The connectivity and the security part is not necessarily the same. I would say, I don't know exactly what Google, I've seen the demo downstairs, but the idea of making software updates over the year is not that, I don't think it's complicated, only Google can do it. I mean, it's.
And maybe.
But it's the same, you mean it's basically going to be using more or less the same?
It's a standard technology.
Okay.
It's like firmware update over the year. It's the same technology, same security technology with the same cryptography that you need to deploy for models of the, it's like updating data.
And there's no tiny update versus big update.
You can, exactly. This is the difficulty when you have low bandwidth communication, is that you need to send small packets of data. Typically on LoRa, you cannot send big packets.
Maybe if I can add, in medical applications, most of the time, the innovation using tinyML solutions, the idea is to keep the information to the patient, not to deploy it to the system, so to answer your question regarding medical application. This is most of the time one of the goals, at least.
And again, I mean, commenting on that, I mean, they're gathering data from sensors which are deployed in the field, sending the data through the internet to some big cloud service, coming up with the modeling and then getting back to countries through governments of, emergency or something. This is the kind of, Google model. The tinyML model would be, working with communities. Like I have some project in Central Asia where there's no connectivity at all. It's in the mountains and they're measuring water level and they're measuring, weather conditions. And the model, of course, will not be as advanced as the Google one, but it would be local. So there's no data going back and forth. So, yeah.
Okay.
Of course, I mean, both have advantages and disadvantages, I would say.
But it is this idea of democratization where we're putting the technology and the control into the local people's hands. And today the idea is that nobody understands the problem like the local people understand it. So they know what they want out of the technology, which is one of the original questions. I think we can end it there. So first of all, thanks for everyone's patience. We will be starting back on time at 2:30 in this room, and we will be hearing about some call outs from the NGOs and the end users about their challenges and what they're looking forward to. So thank you.
Thank you.
Welcome everyone to this session. We will be talking about how we can empower tinyML for NGOs. And we will have 4 speakers today: Nathalie Lesselin, Pad Saxena, Violet Su, and Sebastian Bosse from Fraunhofer. And the first speaker is Nathalie, founder and CEO of Kokoro Lingua, based in Neuchâtel, Switzerland. You want to stand up? So Nathalie drives AI-enhanced language education that supports human needs. She fights for quality education by providing a solution that helps children learn from their peers and is profoundly committed to ethical technology use. So welcome, Nathalie.
Thank you. So I'm really happy to be here. It's very special for me because, to be very transparent, I was not really for AI. Honestly, because I'm working with education, I'm working with very young children, and I was extremely cautious. And at one point, that's why I'm so happy and proud to be here. Thank you for the invitation, because here we are talking about AI for good. And AI for good, this is really the topic for me, especially for kids and education. So I will share where we are today and where we would like to go, the next steps. Alors, je pense que c'est comme ça. Voilà, okay. So what we are doing at Kokoro Lingua, Kokoro means the heart in Japanese. And the idea is to help children learn from heart to heart, from kokoro to kokoro, through a peer-to-peer learning approach. And this is working extremely well. But now we want to move on to the next steps. That means including AI, because we see how supportive it can be. We just quickly won quite a few awards in Paris, in London, Dubai, in Europe as well, but that's not really the point. Today we are talking about children, and we are talking about children's education and children's huge potential. So emotional intelligence. Right now, it's a vital skill for children. The more AI, if I may say, the more AI there will be, the more emotional peer-to-peer human connections there should be, kind of, to kind of balance. And so this emotional peer-to-peer learning approach is essential right now for personal growth and for success. We know that just being a brain is not enough. It's a right balance between the brain, the heart, and I don't know how to say in English, the guts or something. So why are we working with peer-to-peer? Because we know the peer-to-peer, the human-to-human connection is the best way to learn. That's the most efficient. It has been proven by your research that when you learn in a peer-to-peer approach, you memorize 90%, 90% of memorization assimilation. When you learn with 100 students all together in a room, like university or something, just by listening, you learn 5%. So that peer-to-peer for us is essential, not only for the learning process, but for the social bonds that are very important for children right now. So our unique methodology, I was telling children to children for an emotional learning. I will show you a little bit what it looks like. This is in a class actually in Switzerland. This was at the very beginning with a pilot, because there was a dream of helping millions of children learn from each other. And then at one point we had to try to see if it was working. I know. So here, the teachers are the children from the screen. Even if the adult does not hear this is a song, but anything can be taught. This is what we are doing every day. And they are just learning from children to children. So there is this super strong emotional connection because they recognize themselves. It's the same level, same age, no evaluation. So here, this was more to show about the peer-to-peer, how strong it can be. Now we would like to talk about the social ties, because we are teaching through videos. So children are learning from each other through videos, through online videos. Okay, we could think, well, videos, again, screens, again, no screens for children. And we completely agree on that. So what we do is we limit 15 minutes maximum per day. That's the kind of contract we have. Each video is 15 minutes. The children are going to watch the video 3 to 5 times a week. At the end of the week, they will know what has been shown in the video, because they are so powerful minds. They just absorb. So here, I will show you videos again of real life, how it's happening in the classes. How do we create human peer-to-peer connection helped by a screen? Oh, sorry, it's this one. So here we can really see that the children are learning from the little teachers on screen, but immediately we would invite them to reproduce in the real life. So the screen is just showing a way, is helping something that we couldn't do in another way. But then the most important is to reinvest and activate what they have learned. So as you can see, it's working pretty well. It's working pretty well, but we have challenges. And in the challenges is that we have no feedbacks. We know the children learn very well. I mean, we have like a 90% renewal rate. So that shows that it's really working and parents and teachers are happy. But we want to have some numbers to know, okay, how can we better support the child? How do we know how fast they learn? Do we repeat too often? Shall we repeat less? And all these kind of questions, as of today, we can't answer. So that's why we are thinking of introducing AI, and we've done an MVP, like a pilot with that, to help teaching children methodology and reinforce in an interactive way. So the idea is to be able to create that interaction. I will show you a little video after, to reinforce interaction, assessments, and the students clustering as well. So how can we be supported by AI to go more into our objective of education for all children? So what we've done here, why I'm here today, first of all, because we are heavily committed in sustainable development goals, and we know the impact we have whenever we talk about AI. And that's why for us, it does make complete sense to think, okay, whenever we think about AI, let's think about tinyML and how we can include tinyML in our vision. Because if we talk about impact, education, kids, better word, we can't use heavy process and heavy resources. So what's very positive for us is, of course, to lower our impact and to reach countries where we could not go without tinyML. And this is super important for us because you will see right after we are talking about education for all. So where are we right now? As of today, we have reached more than 400,000 children. It's increasing pretty fast. 9,000 schools. We are working with ministries of education. Right now, we won a tender with the French Ministry of Education. We are in discussion right now with 2 additional ministries in 22 countries. Very different countries, by the way, like French, a little bit in Switzerland, but not that much. And then Uzbekistan, and then Japan. So it's completely different countries, but it's very interesting to see the impact that we can have in different countries. So we are right now in Ivory Coast, in Mali, in Thailand, in Brazil. What we are doing, because we have that impact vision, whenever there is a subscription paid, we offer one for free for a family or school in need. So that really allows us to give a better chance to children wherever they are in the world. So regarding the sustainable development goals we are extremely active on is quality education. So we've done 18 months of R&D before developing the program you've seen. Gender equality and reduced inequalities. So that's really our top priority in terms of impact for the SDGs. We have secondary impact because we are part of a group measuring impact, how we can get a better impact on education and on children for a better world. So we have secondary impact, and what I just like with the tinyML is that we can contribute to something else with the 9, the 11, and the 13. So case study, our current program is, as you've seen, just videos of children teaching to children with a few challenges because we can't measure. So we've developed an MVP to evaluate the impact of AI and ML technologies on children's language learning. We are focusing on language right now, and language acquisition, so engagement and acquisition. I will show you, this is really the basic one. So the video is going to show something and the children will repeat. So that's the first example. The children says and we repeat, and we make children speak as much as possible. Now integrating AI. I need to stop this one. Sorry, I don't know how to stop it. I have to say that I like to stop this one, but I don't know if ever. Otherwise, I will explain this one in the meantime. So here, the child has learned what are the fruits. They have learned in English what are the fruits. And now they have to validate and show. So we include the interactive part. They have to validate that they know So they have fruits all around them. The child from the video is asking, can you show me a pear? And the child has to show a pear, otherwise it will say, oh, try again. And so we can evaluate how fast the child reacts. We can evaluate if she knows or not, how many mistakes, when she's doing mistakes, if this next time she will remember or not. So the results are right there. So we've done that MVP and we tested it with 30 children altogether. We have a user engagement thanks to the support of AI, which increased from 60 to 90%. It's huge. We have a child's participation in answering because we have this kind of games as well, but by video, so there is no direct interaction. So we have a rate, participation rate that doubled. That's huge. And a faster assimilation here. So here, honestly, we were a little bit disappointed. And so we're trying to find a better way so that to accelerate this, because we go from 42%, from 33% to 42%. So we think we can still improve this part, but we have a huge impact thanks to the interaction. So here, for us, because we are working with children, ethics is super important. Data protection is super important. So for example, we do not keep in the MVP, we do not keep any picture. We have a lot of picture because we ask the children to validate it through a picture. So we know everything about the child's environment. Sometimes in the, when we first got the data, we could see the father coming, we could see the mother, we could see the sister coming. So we have a huge amount of data. And now we've implemented a way to remove everything. And for the time being, for the analysis, but that's perfectly clear with the families, we just keep the written data so we understand. So, and it's like anonymous, so we don't know who has done what. So we are extremely cautious on that, of course, LGPD, protection of data, and now we are working with dev and technical developers to make sure we can improve that as much as possible, and involving children, of course. So our vision, one of the challenge, by the way, being impact social company is the funding. The funding is really critical. And that's why this is huge in terms of budget. We were talking about during lunch about working with smaller companies or NGO. The funding is critical. Of course, right now, to be able to develop that, we are looking for fundings so that we can develop that approach. Because just being ourselves with the social impact we have and the sales we're doing is not enough to develop a project with AI that will be strong enough in terms of data protection and interaction and impact. So we are willing to integrate tinyML. We are completely open to collaborations with research institutions, NGOs, technology partners to be able to accelerate and reinforce the impact. So you are really welcome to join, come on board. And finally, that's a thank you from the children, because what we are doing right now for me is extremely important. Talking about AI, we are building the future that our children will have to deal with. And that's why AI for good is not just a word for me, it's really the impact that we are having now for the next generation that will change the world, and it's like our responsibility to know if it will be for good or a bit less good. So yeah, we keep the focus on emotional learning, personal connections, and AI coming to support. That's it.
Sorry. I guess we will take the questions at the end.
At the end, okay.
Okay, so the next speaker, we have the chance to have a young talent today, Paz Saxena, who is a sophomore from the Scripps Ranch High School located in San Diego. He is a young founder of TutorPal, which is a platform for sharing shared tutoring sessions between students, who has almost 500 members. and he's the recipient of the first award of his regional science fair. Now his work has turned around generative AI chatbots for tutoring and robotics, and he will be presenting today his implementation of a smart pluviometer system.
Great. Good afternoon, everyone. I hope you're all having a great day. I'm Parth Saxena, and I'm a sophomore from Scripps Ranch High School in San Diego, California. Before we get started, I'd like to express my gratitude to the tinyML organization for presenting this idea and involving me in this project. Additionally, I'd like to thank the company I collaborated with, Apex AI, for their invaluable support and involvement in this project. Rainfall measurement is a really big deal. Accurate rainfall measurement is a fundamental component of managing water resources, supporting agricultural practices, planning urban infrastructure, climate studies, environmental protection, and natural disaster preparedness measures. The data collected is used by a wide range of professionals to make informed decisions and ensure sustainable development. A lack of satellite infrastructure in underdeveloped nations emphasizes the need for ground-based water measurement solutions. The most common industry standard solution today for rainfall measurement is the tipping bucket rain gauge system. The water enters the device via a funnel and fills a small bucket inside before it tips over and it triggers the seesaw to pivot. So that's known as a tip, and it begins filling the next bucket. So this tip triggers, this rain gauge has a magnetic sensor inside, and every time it tips over, it sends an electrical signal, and rainfall is derived from how many times the tips have occurred. So the problem with these devices is that they require manual and periodic maintenance to prevent rust, rigidity, dust buildup, and any unexpected parts from interfering. The high cost of $200 to $600 makes these devices less practical to be utilized at a larger scale. Also, these devices have a discrete resolution, an all or nothing measurement. If it's just barely full, but not enough to trigger the tip, it will not be counted and measured. This problem was tackled by the tinyML Smart Weather Station Challenge in 2022, where solutions to measure rainfall included utilizing machine learning models to process audio signals and spectrogram outputs from raindrops, as well as using an IMU to calculate raindrop size and frequency. So this was actually mentioned earlier today. Aurora was from Team CSIM, and they use microphones with convolutional neural networks to measure rainfall. So we learned from these various approaches and set out for our own attempt at this challenge. A wise man once said, "Keep it simple, silly." So we did just that, keeping 3 goals in mind: low maintenance, low cost, and no moving parts. We aimed for the apparatus to go 6 to 12 months without any human maintenance and recognized a trade-off with the precision and volume of the measurement vessel. After numerous designs, we settled on a simplistic cylindrical vessel with a length of 89 centimeters and an area of 500 centimeters squared, attached to a funnel cross-section area of 1,000 centimeters squared. You might notice these are some very large measurements. We utilize these large standardized measurements as larger openings result in lower statistical errors and larger vessels require far less maintenance, which is what we were going for originally. We incorporated the Neptune liquid level sensor at a length of 89 centimeters and a minimum resolution of 0.51 centimeters of water depth. It uses resistive sensing technology to provide water depth through a TRRS cable. However, a challenge we faced was collecting this data from this sensor. So originally it was intended to be connected to a separate main device, which would then display the values, but we reduced costs by recognizing a linear relationship between the resistance output of the liquid level sensor and the water depth. And you can see this equation here. We derived this equation after several tests through a multimeter. So So now that we recognize this relationship, we implemented an ohm meter module through an Arduino to read the resistance output of this sensor, which we translated to water depth using this linear equation. As seen above, the TRS cable is connected with 2 wires of the Arduino, and that's the unknown resistance. And while this 4700 ohms resistor is known as the known resistance. So the ohm meter module we implemented measures the output voltage across the known resistor 1 and uses this voltage divider formula to determine the unknown resistance of the liquid level sensor based off the input voltage and the known resistance of resistor 1. We use a 4700 ohm known resistor because the accuracy of the ohm meter will be much higher if the value of the known resistance is closest to the resistance of the unknown resistor. So now we have resistance to water depth, to volume, to change to inches of rain in the past hour. So now we have our device. So now that we established and developed our own rain gauge device, the next step was to test and compare its results with an industry standard rain gauge. So we chose the Barani Meteor 200 compact rain gauge due to its high accuracy and usage in agricultural solutions. It operates on tipping bucket rain gauge system, as mentioned earlier, where after a certain level of volume, a bucket inside tips, and that's used to measure the amount of rain. So our testing procedure was actually quite simple in that we left both devices outside for a couple of weeks. And so we collected all this data through the Arduino serial monitor. So after using the chi-square statistical analysis test, we recognize the results were that the differences in data of the 2 devices were not statistically significant. So this is the final iteration of our rain gauge device. So we decided to use a siphon to empty the measurement vessel once full and without using moving parts, and therefore it wouldn't be susceptible to dust or rust buildup. So it follows a Pythagorean cup approach, and once the water approaches the very top, initiates the siphon flow until the measurement vessel is completely empty. So this allowed us to reduce the cross-section area of the device while increasing the accuracy of the device, because a lower amount of volume will result in more height measured by the Neptune liquid level sensor, and thus would result in more precise measurements. So we actually have a video. Oh, sorry.
Maybe you need to pick on the screen.
Sorry about that. It's just
Can you try on the picture there?
Pointer
That's
disappeared.
what he's doing.
It's fine.
That's right.
No, it's
It's like Marshall's law. Something can go wrong, probably will go wrong.
Oh, so you could solve that with a lower language model.
That's all right. It's okay. I'll
Just
just
explain what
speed
you-
through it. Yeah.
Just explain what you-
So
Tell us the story.
in the video, a jug of water is poured down the funnel, which triggers the siphoning effect, which causes the cup to drain the device to drain its entire contents through the base, as shown there. So at the base, you can see, or you would have seen, the water is being released in laminar flow, which ensures the smooth and controlled movement of the liquid through the siphon mechanism, which makes the cup function. So the siphon mechanism relies on a continuous and steady flow of liquid to create the necessary pressure difference that's required to drive the liquid up and out of the device, which is why we chose the specific size to maintain the laminar flow. Alright, so where do we see this going? So further modifications can be made to the measurements of the device, such as changing its height, cross-sectional area, and catchment area to make it better suited for locations with varying amounts of rain. The liquid level sensor we used comes in 3 different sizes, which can reduce costs even further, as the originally large measurements are now unnecessary due to the siphon mechanism. So devices like these can be positioned in several local regions with different elevations, climates, and habitats to collect and report data collected on rainfall. So we can utilize LoRa or long-range technology to develop a centralized system of multiple rain gauge devices as it is a method of transmitting data and connecting devices at very long distances at low energy input. The data from these devices can then be stored in cloud networks for professionals to make decisions for sustainable development. However, it can also be used to develop and train advanced artificially intelligent models capable of analyzing this data and making accurate predictions for human needs like agricultural, urbanization, water management, and natural disaster preparedness strategies. Oh yeah. So where does tinyML come into all of this? So we hope to deploy smart rain gauges equipped with tinyML models in the field to collect real-time rainfall data. By embedding tinyML models directly into these rain gauges, real-time data can be collected and processed locally. And this minimizes latency and allows for immediate insights. A specific agricultural use case of this is farmers can receive real-time alerts about soil moisture levels from these models, helping them make informed decisions about when and where to irrigate, therefore conserving water and improving crop yields. So we presented existing solutions for ground rainfall measurement, as well as the design and setup of our sustainable system consisting of a low-cost, motionless, maintainable, and accurate rain gauge. We compared its performance to an industry-standard rain gauge, the MediaRain 200 Compact, developed by Barani Systems. And furthermore, we displayed our more robust, small, and accurate final iteration with a siphoning technology, as well as the practical application and communication of such devices. In the direct future, we hope to collect more data to fine-tune the resistance mapping of the liquid level sensor and train machine learning models to aid in predictions and analysis of this rainfall data. Lastly, I'd like to let you all know that all our work is open source and we will be sharing our designs, code, and list of parts for anyone to build upon this work that we did. So thank you to the tinyML organization for the opportunity to work on this project. And thank you to the ITU AI for Good organization for having me here. So that concludes this presentation. Thank you for your time.
Thank you, Pat. We will ask questions at the end of the session. And our next speaker now is Violet Su. Violet is a business developer at Seed Studio, where she strengthens the partnerships between the academia, the industry, and she is very involved in the Tech for Good activities that are running at Seed, and she will be presenting today how Seed hardware can help the tinyML community.
Thank you. Hi everyone, good afternoon. I'm Violet. It's such an honor to be here. And a funny story about it, I joined Seed on May 15th, and it is the day about like a tech transformation like this and imposed by ITU. So I wrote a little diary almost every year about, oh, this is the day to celebrate. And now this year I'm at ITU to present about technology for good was like, is it something that is really destined? But another fun thing about it is like when I'm in the tech world, many people are talking about how much they like Python or C# or other languages. And I was like, I learn language, but not that type of language, more like English. And I can say, je parle un petit peu français, but this is the kind of language that I learn. So I'm not from the technical background. And then I think if I present about technology and then I understand it and I can use AI, then it means a large percentage of people can use it too. So my title today is Accessible and Actionable ML for like tinyML for a better future. So I will share a little bit about our company and about like some of the trends that we observe as well as our approach to make it more accessible and actionable. So a little bit about the company is C Studio with 3 E's. One of the is like the seed of electronic, like the seed of innovation. And we are founded in 2008, and since day one, we provide open source hardware for people to validate your idea. You can take half a day to put all these different modules together to see whether this idea works or not. So this seems to be able to open up the possibility of like different kind of innovation. But along the path, we notice many people come to us and say they need more robust devices that can be put in the field, like data modules like this can work in the proof of concept stage, but if you really want to deploy in the field, maybe there's a longer path to validate and make it waterproof, dustproof, etc. So a few years ago, we began to develop a lot of devices that can be put in the field to run a few years. So here are some of them. So we begin to see how we might be able to cooperate with our partners with different kind of technologies, and we can improve the productivity. So, and for us, what we provide, if you come to our website, there might be more than 1,000 products, but they can be categorized into 2 main categories, sensor network and edge computing. So for sensor network, we provide a lot of sensors that you can collect data, and network to transmit data by different kind of protocols from Wi-Fi to Bluetooth and LoRa, etc. And then for edge computing, is more about processing the data. And this is the business model of the company. So we are in the middle. We integrate different kind of emerging technologies and turn it into hardware products. Some of them might be little modules so that you can build your hardware more conveniently. Some of them are robust devices that you can integrate your software with it and provide as solutions that can be put into different scenarios to serve the digital transformation of different industries directly. And here are some of the outstanding product lines that we have that comes from different categories from open hardware to robust industry devices. And we have been embracing and dedicated a lot of efforts in the sustainable development goals. So our mission statement is to empower everyone to achieve their digital transformation goals. I will share a little bit later about that. And before I dive into the trends and our approaches about tiny machine learning and AI, I would like to share a few projects that is coming from the community or from our industrial partners. So this is a project that is using tinyML with little devices like this microcontroller with different sensors, and then it will enable you to detect early warning for flood. And the second one, this one is also coming from the community, and it's called the ESP espresso scope. So it's like a little espresso cup, but then it allows you to do like microscopy experiences, like experiments. And it comes from the community, and it's modular, it's open source, very affordable. And they have been conducted workshop worldwide in Africa, in the US, in Europe. And I really love one of the co-founders quote is that if your solution works perfectly 6,000 kilometers away without you being there, which means it's quite solid and reliable. So that is like a different iteration of the version of this microscopy. And now we are talking with them about making it into this like handheld instrument, and it will be provided more easily to people all over the world instead of like asking them to assemble them. So the modular version is still available for people to get hands-on and then build them. But this version will be available for anyone who can purchase and use immediately for citizen science, for different kind of research. And they use this little module in it, so it can do tiny machine learning to collect data decentralized in a decentralized manner, and to share the data and share the models. And this is an application in Sardinia Island of Italy. And so we deploy industry grade devices in the city at like more than 500 sites. And what they get is on the one hand with the Wi-Fi sniffer to monitor the crowdness of the city. And the second is to deploy the weather station so that they get microclimate data. So for this, like for the crowdness, we have seen some news about during some holidays or some of these high, like peak season for tourists, there might be some accidents because there are too many people in specific spot. So they are able to monitor that and to prevent risk. Or on the other hand, if with that, they will say, oh, we might need to add extra buses for this route, or maybe that route doesn't have many people, so we reduce it or even remove it, so they can better design the city. On the other hand, with the microclimate data, they are able to monitor the urban heat island. So this part is hotter than the other part of the city. So maybe they need more green land. Maybe this building is dark, so it absorbs the heat. So they need to paint it like in light color, so it will be able to aspect the heat more efficiently. So these are the products deployed in the city, and then they are building AI models to monitor the heat wave and to provide insights about how to better manage the city, provide better experience for the citizens as well as tourists. And this is another project. It shows how we iterate from the very beginning to like new version of products. So we have this little product. It has a tiny camera on it, and it can do like animal detection, like cat or dog. And we were thinking, if it can detect cat or dog, how about it can detect a larger cat like panda? So our founder is from Sichuan province of China. So we, but this one couldn't be deployed in the forest. So we developed this one, and it has camera, and it runs, it sends data by LoRa, but images couldn't be sent by LoRa because LoRa is only for low power consumption. So we actually run the tiny machine learning on it, and it only sends the result like yes or no, yes, a panda, no. And then they went there, deployed it in the field. But then later we realized it's not that very easy to use because you need to like with the training of the model as well as like a collection, etc. So when we receive feedback, we actually will build a new version of it that can not only use for like as is called a panda sensor, but also for like meter detect, like reading the meter or like other kind of detection as well. So for us, we really embrace the needs from the community and listen to the needs and see how we might be able to cooperate and build some new solutions that can specifically cater to some needs. And then coming to tiny machine learning, today we are in this workshop about tiny machine learning, so I don't need to give the definition about it, but the trend that we notice and also or what is needed for a more sustainable or more accessible tiny machine learning applications on the one hand is multimodal. So you need more parameters, you need to collect more diverse data. And also we needed to be faster, to run faster on a tiny MCU or like lower power so that it does not constrain on in the room here with direct power consumption, but it can be run on a battery and put in the field, or easier to use, like you can train your model more conveniently, and it is cheaper so that it's not like, oh, I couldn't afford that, something like this. So here are some of the trends as well as how we embrace it and develop our products and services. So coming back to multimodal, we need a lot of parameters. So we have currently, this shows some of collection of our sensors. We have about 400 different type of them and growing with many more. And on the other hand, like those are tiny ones, single sensors, but we also have multiple in one sensors that can be robust enough to deploy in the field to collect multiple data in one. And also when it comes to smaller and cheaper. So we have these little microcontrollers that range from a few dollars to maybe $15, and then you can use it to run tiny machine learning on it. So this kind of MCU is tinyML ready. And when we think about it, about like the title is add AI to almost anything. So if you have a bunch of sensors, you have a bunch of different microcontrollers, and you have different kind of models. When you combine these three different elements together, then there will be endless possibilities. An example is like, for example, we have the same camera, the same microcontroller, but we put a different model for it. So this can be a sensor for bird watching, or it can be another sensor for intruder detection. So this is the kind of possibility that we can implement. And so, and also we, with the technology development, we embrace and develop more and more MCUs that are faster and lower power consumption. And also when it comes to easier, we would like to implement no code ML operation. So you do not need to write a line of code, but maybe with the web server or with talking to it and then give it a new task, or like only a few shots that you can train a model instead of thousands of pictures. And so we have this platform called the SenseCrowd AI, and then it will allow you, on the one hand, there are public models that you can use immediately, but we also encourage users to share your model. If someone else uses your model, you can share a profit of it as well. And also there are encouraging of different cooperation that we can work together. And so, and of course, when we talk about AI, like generative AI is a buzzword, but it's not just a buzzword, but also adding a lot of value to the real world. So we have a lot of devices that supporting large language models or other large models. And when this convergence of tinyML and generative AI come together, it comes to this embodied AI. And what we are trying to do is we would like to see tinyML as the trigger for large language models. So an example is, this is a product we launched last month. It's called a SenseCap Watcher. So what SenseCap Watcher does is it has a camera and then can take a photo, and then usually the large language models, like the device is running the whole time on the device or on the cloud. But then if it's running the whole time, either it's very high power consumption or it's consumed a lot of cloud. So we don't want it to run the whole time. What it can do is with this camera, if we do it for like put a tiny machine learning model on it, and it's running person detection. So if there's no person passing by, the large model doesn't work. This one keep watching, and then if it detect person, it send that keyframe to the edge device or to cloud, and then it begin to run the large language model and tell you what it is. And then this is not just constrained to camera. You can connect to temperature, you can connect it to humidity, and then those kind of specific data will trigger the large language model to work. So this is an example of like how easy it is. You can push, like press the button, talk to it, and then it will run a new task, and then it will work for you directly. So I regard this tiny watcher as like extend your eyesight, like extra eye or extra hearing or extra sense that you can see in the real world. And so we call it the Rhapsody of tinyML and local LLM. And my colleague wrote a blog about it and introduced how it can be an efficient way to run AI more cost effectively, sustainably. And so apart from the products and services, we also provide a lot of like put efforts in support tinyML. So there are a lot of workshops that we conducted worldwide, like different workshops in different countries. And we also host some online and offline events. And then we provide some of the hardware for people to build applications to support tech for good. And so this is our efforts for SDGs with products, with our expertise, with our personnel, as well as directly involved into events or hosting events. And we would love to cooperate with different partners, from individual to community to academia or startups. And our expertise is more in the hardware, but we would love to see how we can cooperate together to build solutions for different applications. So let's thank you. Like I have this microcontroller with camera and mic with me in the booth downstairs. So if you have any projects that you want to use this for tinyML, I have a few of them I can give to you so that you can play with it and build some applications. It's just at the entrance of the AI art gallery. Thank you.
Thank you. So the last speaker today is Satan Bosse.
Yes.
The head of Interactive and Cognitive System Group Fraunhofer in Berlin, Germany. And he is also a lecturer at the German University in Cairo, a board member of the Video Quality Expert Group, the advisory board of the International AIQT Foundation. So he will be presenting today how tinyML can be used for good for agriculture.
Thank you. So, and also thank you to the previous speakers, so especially to Pat and to Violet. So I think this builds very, very nicely upon what you just told us. And I use the camera similar to yours on an ESP32 to put it in a birdhouse in my garden to record birds while nesting. which is great for the kids to take a look at. Okay, so let me ask you a question at first. So I asked ChatGPT here to give me a visualization of what agriculture might just look like in the future using tinyML. So would you share this vision? Mostly it's no. Yeah, sometimes you find very, very, very optimistic people, but it could be very noisy.
So use a lot of energy.
So what I would like to talk to you about today, so first thing is, so what is special about agriculture? We heard a bunch of these things already. And I want to build upon that to give some example on tinyML and then talk about some platform aspects to bring these things together. And then I would like to shed some light on the use and the role of interoperability. So first things first. So if we take a look at the history of digitalization, and we take a look at agriculture, where it seems to be rather slow, then we can ask the question, so why is that? And one example in comparison is the supermarket. So like 2 generations ago, more or less, in the supermarket, everything, if it was so-called supermarket back then, actually, everything was mostly pen and paper. And today we have these self-checkout cashier desks. This is a very Western perspective. I can tell in Germany it's like this. So most of this is still pen and paper in agriculture. And there is some digital aspect to this. And the digital aspect comes into play when the farmer takes a picture there and sends over this thing with WhatsApp to his neighbor. That's the only digital part in the documentation. I'm exaggerating a little, but it's not so far from reality what I'm saying. And so why is this actually? So this part of this is the heterogeneity of the ecosystem. So this is just the example of the different soil types that you find in Europe. So you can see that the soil, which is obviously a causal factor in agriculture, is super heterogeneous. And if you take a look at the weather, it's even more so. And if you then, from global perspectives, take into account like economic scales or socio-cultural and socio-economical things, traditions in agriculture, then the possible space of ecosystems is expanding even farther. It's super heterogeneous. And let's do this comparison again. So if we're talking about the heterogeneity, then we're talking about almost 600 million farms all over the world. And most of them are smaller than 2 hectares, so smallholder farms. And these farms, they cannot be neglected because this amounts to 30% of the global food supply. So this has to be taken into account if you talk about digital agriculture. And if you compare this now to other sectors, then there are about 6,000 airlines in the world. There are about 25,000 major bank groups, about 20,000 supermarket groups. And in this sector, for example, the pilot has no say in the decision of applying a digital tool, be it AI or something else, in the airline. That's actually one person, maybe a group of persons per airline. So if you were a startup, you could do this in a lifetime, talk to every single one here. This is impossible if you think about agriculture. And so what's happening here is, given this heterogeneity and the number of people that are involved here, because every single farm is a business, you have about 540 million systems, because every single farm is a system with configurations of potentially tinyML models. So let's go through some examples, and I can do this very quickly because I'm very thankful that you gave us some examples already. So here is from a research project of us, an example where we have this autonomous robot that runs through an apple orchard, and it's basically automatically estimating the ripeness of the fruits so that the farmer is informed when to pick them, ideally. This is an example of the apple quality recognition here from this project. And this runs on a tiny module. So in our case, it's a Raspberry Pi with a Jetson stick. So it's run about 5 watts that we use here. And same thing applies for drone flyover, for example, for pest detection. So there we have the AI module, so the insurance machine, how we call it, directly on sitting on the device, because here you have this energy constraint, right? So if you have if you cannot do is exactly what you said in the connection of LoRaWAN. If you have to store all the data here on the device, then you need a hard drive, which is heavy, and then your operation time will be lower. So you want to have as little weight here sitting on the drone at the same time, just to increase operation time. And at the same time, you don't want to spend a lot of energy on the processing on device. So this is where tinyML plays a major role as well. Here are some examples of the yellow rust detection from this project. And this can be applied, for example, on sorrel detection as well. So sorrel is a plant that you don't want to have in the field because it's poisonous for cows. So you want to make sure that it's not growing where you have your cows. And this can be done in this very safe way. So the cameras might be applied to a drone or might be applied to some sort of robot or some other machinery. And then you can directly detect this with very, very small models. Here, this is an example for soil monitoring. So we should catch up later. So maybe your approach is something that's interesting here as well, because we have these modules that you really stick into the soil to measure the soil moisture in this case. So it's not so much about the rainfall, but the moisture plays a role here. And then it's connected to the base station with LoRaWAN as well to transmit the information that is gathered here from the sensor. So these are all aspects that play a role here. And these are basically modules of a system configuration. And depending on your budget, depending on the conditions you are in, and depending on the sort of form that the type of agriculture that you want to do. Do you want to do like conventional one, traditional one, or do you want to make something like organic food? You will have a different configuration. And if you take the farmer now into account and ask them, so what is it actually for you that is the greatest obstacle in digitalization of the food industry, then this is the result. This is from Germany. I'm not sure how good this applies to other countries, but I guess that for most industrial countries, it will be very, very similar. So there is the susceptibility to failure. There's high complexity, obviously, insufficient connectivity. There's data security. There's lack of technological maturity, high investment costs, and lack of, digital competence. And what is it that tinyML might actually bring us here? So if you have these small modules that are not super complex, then the failure probability drops. So that's something that can be addressed here. Insufficient connectivity is not so much an issue if you use like LoRa-based protocols or if you do all your inference on device, because then there's no data to be transmitted at all. Data security is not really an issue if the data is not leaving the device, if it's just basically analyzed there and you just get the data product. And obviously high investment costs, I think you mentioned 10 euros per device. So that's totally different to a GPU basically. So this is something that tinyML can be of real use for agriculture. But then there is this thing, how to bring things together. There are some aspects left. So there's the high complexity. And I can imagine that if I have like a bunch, like a Lego box of tinyML things, and I'm a farmer, then I would feel overwhelmed. So this is complex. How can we address this? And then there is the lack of digital competence. If I have this Lego box of tinyML modules, then I need to bring this together. How can we do this? And this is another aspect that we are working on in a project in Germany as well. It is called Nalamki. It's funded by the federal government. And here we are thinking in some sort of leveling. So we have 3 levels. We have the machine level, that's what we call this. This is sensor level as well. So this might be data from satellites, obviously not tinyML, but it might be like devices and modules sitting on top of machines as well. Might be sitting on drones. And they are connected with a local cloud, or local, whatever you call it, edge, where processing that is more heavy can happen. And then this, if the farmer agrees, so that the data sovereignty aspect here, this can be shared and the models can be updated with like something like a central system, 3rd layer here. And it's sort of nice if you think about tinyML and if you think about the obstacles, because it directly addresses inherently the updates of the models because they will improve, and you want to make sure that your set of modules are up to date, at least sufficiently, and it is able to adapt this directly to this heterogeneous ecosystem, because it doesn't really matter what is living here as long as it's sort of compatible to the system and can be plugged in. And it's a great sort of complexity reduction. This is inherently the same thing as tiny models. What I mean by this is that the complexity is basically reduced at the machine level here. And since this is one system that can be used by one dashboard, by one interface, by the farmer, there is a certain mitigation of lack of digital competence, so because it's just not necessary. And so what we're doing with this right now is to identify use cases and application scenarios in different contexts, in different systems. Right now, we just moved this in March. We moved this to India, to Hyderabad, where we take the same framework and just plug in other models that are more appropriate to the use cases and the agroecological context that we find there. And obviously, we are continuing developing the corresponding tinyML models, so low power AI models. And these models and the data products are then basically integrated in the whole ecosystem. This is just a quick, short glimpse of what we're doing in India, because this is sort of interesting as it directly connects to capacity building here as well, to make really sure that we have the perspective of all the people affected and involved in this process as well. And one thing is relevant here. Obviously, the necessary condition that this works is interoperability. And the necessary condition that interoperability works is standards. And this is something that we are lacking in agriculture in both sense, in terms of normative standards, so how do protocols and data models and AI models actually work together, but also in terms of analytical standards. So if we talk about biodiversity, for example, say we have a system and we want to make sure that this production system is sort of, it's an agroecological system, then we have to have a definition about this. And this has to be a definition that's some sort quantifiable as well. So we need standards for this. And at the same time, agriculture is under pressure because we are sort of on bad trajectories in terms of climate. So food supply worldwide is endangered, if you want so. And so this is why the ITU and the FAO 2 years ago founded the AI and Internet of Things for Digital Agriculture Focus Group. And what we're doing there is to identify use cases. tinyML is in here as well. Key concepts, gap analysis, standards, architectures, community building, and this leads to guidelines. Next meeting will be in Utrecht in about 3 weeks. And before that, we have a workshop as well. So if you want, you are welcome to join. It's an open platform. Everyone's invited. And yeah, so this brings me to a close already. I guess the summary is clear. So tinyML plays a major role and has a lot of potential in agriculture. Thank you.
Thank you, Dr. Bosse. All the speakers kept time, so the thing is we still have maybe 5 minutes, I guess, Thomas. Not here anymore. So I invite just the speakers to come and take questions from the audience. So Sebastian, if you agree. So anybody, a few questions? Yes, Marco.
Oh, I have one question about e-learning. So, I mean, first of all, I mean, it's not only valid for children, but also for adults. So when we organize the courses, people work together and they solve it. But the question is about the image recognition system you showed on the tablet. Is that running on the tablet or on the cloud?
On the tablet.
On the tablet. So everything is contained on the tablet. So it will work offline.
This is a target to make it work offline, because in I would say like South countries, it might be more difficult. The challenges we have in Mali, in Peru, in Brazil even, is that there is no internet connection. or the quality of internet connection is not enough, and we don't have it. So that's one of the biggest challenge, because the easiest way is to do on cloud, but in reality, if we want to have the impact, we'll have to find a way.
Okay. Last question. Is the size of the screen important?
For children, yes.
Yes,
The
okay.
phone is a bit too small.
Okay.
So we better have like a tablet. It's
Okay.
more efficient. We tried both, but we don't have enough. We would need to try with more children. Like 30 children is not a lot. It showed us that the impact it has. So, but we need to do the test on many more children now.
I have one question. Oh, great presentation. I wondered, just out of interest, that resistive structure you're using, how expensive is that? You said it was a kind of cost element in the whole solution.
Right. So the largest one,
Yeah.
about 90 centimeters,
Yeah.
was $100. So that is expensive. But the smallest one, because after the siphon system, the size of the height of the measurement vessel is sort of it's not that important now. You can use a smaller device. So the smallest one is 11 inches, and I believe it's around like $20 to $30. So
I think we should talk. I think there's other ways of doing that. So.
Okay.
Questions? I had one for you, but so your actually it's a bit linked to what Sebastian said about the things of shipping these small pieces to, let's say, farmers, like a Lego box. You use the term Lego box. Then do you have resources that people can use to actually build something out of it without having strong engineering background or plans to educate people to use these small.
You mean the small devices?
Exactly.
So I think I hope I understand it correctly. So I think if it comes to when you like Sebastian mentioned about the farmers, it might need some like structural parts that like for deployment or installation. Then if in that, I think locally there might be some lab that they can produce like locally with 3D printing or something for the parts. But for the tiny machine learning that I mentioned about make it easier for people to use is actually for us to remove the part about coding or like so they can like just with clicks like connect to the laptop and click and then with still a few steps the model is running on the device and then you can test it. So this is the part that we want to remove so that they don't get worried about writing a line of code even though it seems simple for engineers, but for normal people who doesn't know, it might be difficult. So for us, it's more about like no code experience, but not the part about how to make part locally. So did I answer you correctly?
I have a question on more on the agricultural aspect of it. It's been covered by two of the speakers. I'm just trying to. We're always doing the sort of Lord Kelvin. If you can measure it, you can improve it type methodology. But I'm just interested. Has there been any access to go beyond that in the idea that, how do we get people to use resources which is good for the collective rather than individually? Is there any? I see that you're working with like the federal ministry. Is there any discussion about how with that information we can actually make ourselves more resilient for the future as opposed to just okay we save water today but maybe looking a little bit more long term in terms of the collaboration and if there's any possible impact on that, or also is it that they can I put it in a very nasty way, but like say I know that it's going to rain in my field first. Is it I'm going to get advantage? Are we sure that this is being used for good in one sense, or how are we making sure that these tools are being used? We hear of these awful things where we're growing, I don't know, avocados or nuts or something, all these things we shouldn't be doing. So I'm just curious, is there any link now between what you're doing and the policy of the future? Big question.
I guess I never really considered it for the long range sort of thing. The way like we thought of it was just to be used in like locally, like local farms, and we didn't really consider it being used for any negative usage. So,
or positive. Okay.
Yeah.
Is this recorded?
Yes, it is.
So then,
Get coffee.
there is a certain lack of convergence in terms of technical possibility and regulatory considerations. So this is what I see, and I guess that so this basically leads to suboptimal incentives for individual farmers. This could be improved, but it's very difficult to do so because there are reasons for these incentives. So they have a history and a trajectory as well. And people perceive them, some people perceive them as privileges. Privileges are hard to give up and hard to be given up. And so I think that we are in some sort of, let's say, suboptimal situation. Technology might just be able to lead us out there, but it's a lot of work also on the policy.
As the competition, the challenge tinyML 01 smart measure station stated, we had a problem given to us, which was quite very interesting. Like the traditional weather measurement instruments were utilizing moving parts in them, which were quite inefficient in some aspects, and we had a problem of solving them. The CSEM Aurora weather station, uh, which was quite very efficient in its first iteration as well. It performed, had major breakthroughs, and we were given a challenge to attempt to at least attain some things and beat it through some of the challenges that it had faced. So the main aim of this project was the same: build a weather station which relied on stationary aspects of measurements and parameters that could help analyze the weather patterns accurately, and then predict or classify between the weather states that are currently present in the environment. So and obviously the uh, measurements had to be accurate, the predictions had to be precise, and they had to be in accordance with the actual ground values that needed to be verified, and then only the values could be taken into further considerations. So yeah, so the goals and objectives. The first goal was to collect the data. Collecting the data, as we know, is an important aspect of training any kind of an machine learning model, whether in the case of classification or regression, whether we want to predict something or we want to classify into multiple labels and classes. So the collection of data was quite a tricky process, because collecting samples of rainfall, samples of winds. So focusing on the rainfall aspect, not quite a lot of help from the environment itself. There was no rainfall for the past 2 or 3 months. So we had to rely on artificially acquiring the samples by setting up an environment in terms of the basic necessities that we had in our surroundings. So by collecting the relevant rainfall data and making sure that it was accurate enough to classify into multiple classes, and the features that it generated were able to relate to the actual ground realities, then comes the aspect of model training. So now once the data we have collected has been gone through the initial pre-processing filtering process, then the DSP analysis and feature generation aspect, we get to a part where we now have an array of objective values that are ready to be fed as an input into a model, and hence the model needs to have a precise and accurate step-by-step layered architecture. If now, as in this case, we have used a neural network architecture, so the layers of the neural network, each neurons and each each functions like convolution or max pooling or ReLU, etc., had to be implemented at precise steps to get to precision. Finally comes the aspect of result in the sense the data which had been collected, the model which had been trained, and the parameters which had been measured from the environment needed now to be displayed in a way which was quite accessible and quite acceptable by the people, and it had to be readable enough because the values that were currently being under processing were generally normalized values. They were not some values that we could access and we could infer from. So the result aspect deals with creating a dashboard which had to be publicly available and hence could be used for classification analysis. Now coming to the data set, was a total of around 15 minutes, which was then filtered to around 10 to 12 minutes of data, out of which 9 minutes was purely for training, and the rest of the data was for the test set. There were three classes of rainfall, that is the high rainfall, then the moderate or the mid rainfall, and the low rainfall. So each frame of the data set was around 10 seconds, and the uh, number of such frames were around hello, am I audible still?
You're back.
Yes, you're back. Yes, go.
Yeah. Okay, sure. Yeah. So yeah, as I was saying, the frame length was around 10 seconds, and uh, the training windows were around 1395. The input frames were 10. Intervals was around 1 second between each of the frames. The lower frequency value was 300 hertz. The center frequency was around 8200 hertz something, and bandwidth was taken up of around 200 hertz plus minus 100 on the upper and lower side. Then analysis of the data set, analyzing the ground values to determine whether or not the data collected and the model that had to be trained was actually efficient in calculating what the ground reality was. So basically basic analysis by measuring the water that was collecting the water that was stimulated as a rainfall in the same aspect as it is generally measured by the meteorological department. A 10 centimeter gauge was taken to a 10 centimeter diameter gauge was taken to collect the water sample. Then by basic formulas, it was calculated the height of the water in each each indicated intensity case were calculated hence, and this is actually data of around uh, 15 to 30 minutes of continuous water flow, and this indicates I think this indicates the hourly analysis of a rainfall. So if per se, if I'm saying the intensity of a rainfall is high right now, so that means that the uh, if the same intensity follows on for 1 hour, the water collected in the gauge would be around 24 millimeters. Similarly, for mediocre or medium rainfall, it will be around 16.5, and for low rainfall, it will be around 5.4 millimeters. Now coming to model accuracy. Now, as indicated, the training data was quite low because, as said, the water had to be stimulated, and there were some resource constraints because we were not able to waste quite a large amount of water. So some constraints had to be implemented on collection of data, and hence it was quite unpredictable whether or not the model may have the required accuracy or not. But through an iterative approach, like increasing the data set by iterating it on each and every step, we got to a point where we were able to have an accuracy of 97%
Okay, the
attain
10 minutes
accuracy.
is up. So can you finish in 1 minute?
Yes, yes, yes. It is about to get over. Similarly, model accuracy and the final part was of deployment. So deploying the entire architecture in wireless medium, it was analyzed that the battery life was required of around 2 to 4 days by calculation, and the cost of the entire architecture comes to around $85 with everything included. Uh, I had one video demonstration. Just
Are you sharing something?
yes, sir. Just I'm sharing something. Is this audible?
Yeah, you can
Yeah.
just speak on it.
Yes. So this is the video demonstration that I am currently showing. The first classification is of a high intensity rainfall. After which, as you can see currently, it has come down to toggle to a low intensity rainfall. The uh, sound clarity will be quite indicating in what the two classifications indicate, and apart from this, the F1 scores indicated that an the error between the high and low classes were quite high, but that was not predictable because the predictable value should be the errors between high and medium had to be high, but this was due to the toggling inefficiencies in the stimulated environment rather than the model training approach. uh, and uh, yeah, so apart from that, the model performed well in testing phases as well. Real-time testing, it successfully implemented. Uh, apart from
Okay, thank you so
and
much.
yes, thank you, sir. Thank you so much. Apart, just one single page I had to show.
We have run of time, so I'll skip. I have to go to the next person.
Okay, sir.
Yeah. So next is okay, can you stop sharing the screen? Yes. Okay, Dennis, are you there?
Hello. Good
Hi.
afternoon.
Can you please
Yes.
be quick on your presentation? We are running out of time. Yeah.
Okay. Thank you. Listening to my screen.
Yes.
Okay. All right. Thank you very much. So please, we are Team Gemstone, and we are to present on our challenge. So basically, going to take us through the problem statement, some of the objectives, our data set, our approach, the results, and our feature direction. So basically in agriculture, we have reliable weather monitoring. It's crucial for productivity, especially in remote areas. Existing stations usually are very costly, and then maintenance is intensive. So we are proposing a low cost and low power and an accurate weather station with our moving parts. And we are focusing on rain and then the amount of rain that we can measure. So our solution is going to leverage edge impulse, edge machine learning, and ensure an easy installation and then maintenance. Okay, so basically this work is aimed at prototyping a low-cost, energy-efficient weather station capable of measuring environmental conditions, which includes rain intensity and then the rainfall amount. Okay, as the challenge states, it's supposed not to have mechanical moving parts. So with our methodology, it involves we using a deep learning algorithm to build a small size classification model that can be deployed on an Arduino Nano 33 BLE Sense platform. So basically, we acquire data, we process the data, we design the model, we train and validate the model, and then we implement it on the hardware device. So basically, we focused on using Edge Impulse platform to achieve our results and then deploy the model. So for our data set, the data set we utilized in our project was gathered by AI for Africa, which was in Kogi State, Nigeria, which comprises of audio recordings captured using a galvanized zinc sheet over 12 days in September 2022. Basically, these are some of the properties, some of the things they did in here. They used the TechnoSpark 7 MP mobile phone to do the recording, sampled it at 2205 Hertz. And then the number of samples they collected was 25, which was 5 minutes per sample that they used. Basically, we took their data set and we were able to categorize the data set into a very heavy rain, moderate rain, low rain, then no rain based on these rainfall intensities. And then we're able to split the data into training and testing sets of a ratio of 74 to 24. In terms of exploring the data, after loading the data to Edge Impulse, so you could realize that if you look at the frequency of a very heavy rain, which is shown clearly here, we have low rain, no rain, then we have very moderate rain. This is supposed to be heavy rain, not very heavy rain as seen here. It's the typing mistake that we made in here. So basically in the model development, we selected a neural network architecture for our rainfall classification, which was based on a 1D convolutional neural network, which involves 3960 features. We have a reshape layer of 20 columns, a 1D convolutional layer. We have a dropout layer, another convolutional layer 1D, and then dropout rates, and then we added a flattened layer to it. So our model we selected is tailored for rainfall intensity classifications for audio files. We optimize both robustness and efficiency, unlike using a fully connected network where which architecture would effectively capture temporal and spectral features of audio data without excessive parameters. Okay, so moving forward, we trained the model, and the training process involved optimizing the neural network parameters. We trained it for 100 cycles with a learning rate of 0.005, and then we used a CPU for that. And in training, we had an accuracy of 99 with a loss of 0.07. So moving forward, we tested the model on the training set, and then we had an accuracy of 97.47, and then a loss of 0.01 in that sense. So we moved on to deploy the model on an Arduino BLE Sense, which you can see the specifications of the Arduino BLE Sense. And on the Arduino BLE Sense, we actually have a microphone inbuilt on it, which is the MP3 4DT05 microphone, which we can actually use to pick sound, audio sound. So in deploying the model, we actually deployed the model as an Arduino library file, which we had to then add some other code to it. So you could see in a quantized model here, we have the RAM, which if you compare the size of the RAM to the size of the RAM of the board itself, which is quite significantly very less, which proves that we can actually deploy the model on the Arduino BLE Sense. So basically in our deployment, which we deployed it as an Arduino library loaded onto the Arduino Nano BLE Sense for real-time inferencing. So what we have here is actually the Arduino BLE Sense, which is connected via a USB port to our laptop. So basically we just enclose it in here so that water would not be able to spoil it. So this is it with we opening the cover and the cover being closed. So basically deploy it, you actually see something like this in the Arduino IDE library interface. And then, yes, so basically that was how we achieved this. So I'll basically play a demo of what we did in live testing. So we actually played the environment at a shower, which we had different sets of rain scenarios, and we could detect that and also measure the pressure and temperature of the environment. So I'm playing the video. I think sharing my screen, the audio would not come, so I'll try to talk through it. So, okay. So basically, this is the Arduino Nano BLE Sense with the cover opened. It's connected. Okay, give me a second. It's connected to the laptop via this USB cable. Okay, basically. So which we can record the values via the serial monitor, as we can see in here. So if we look at the showers right now, basically we have like low, and then you see that each time we have a demo for no rainfall over here, basically. So we could see with no rainfall, and the values recorded in there as no rain, with the temperature and the pressure being measured on and seen at the serial monitor. If we have a light rain in real time, so you realize that we can pick that from the serial monitor as well. Okay, which we have light rain being detected at instant to measuring our pressure and the temperature as well. So if you have a very heavy rainfall, so you have that detected as well. Okay.
I think that should be good, right?
Yes,
For the
please.
demo.
Yes, please. Yeah. So this is the end of the demonstration that we've done. Okay, for the work.
Thank you
Okay.
so much.
So yes, come again.
Yeah, I think we can finish there. Thank you so
Okay.
much for the presentation. So
You're
I
welcome.
have
Thank
one comment for this competition. We've seen that we have run this, I think, 3 iterations of the competition, but wind is a challenge. Seems like it's difficult for teams to crack wind. It's only rain, but no wind. So we are going to continue running this competition. We're going to open it now for a long time, because most of the times we are opening it for 3 months. So we'll open it for the rest of the year. But of course, we are going to reward these teams for their effort. They have done quite a good job. And we can see that from 3 classes, now it's up to 5 classes. So it's quite an improvement. But we are going to open this competition for a long period of time to see if maybe some genius can come up with a good solution on how we can crack the wind problem, because yeah, wind is a bit of a problem. So for the 2 teams, Genstorm is the winner. Of course, partial winner. And ADD is the runner-up, partial runner-up. So congratulations. Yeah, well, thank you everyone, and I hope we had a good time in AI for Good Global Summit, and thanks for contributing to the conference and to the workshop on time. So maybe if you have some closing remarks.
Sure, yeah. So I don't know much to add, but what's nice to see is the passion actually, and the belief that AI can be used for good, and that tinyML has a big place to in this transformation. And I think we come back to the idea that we're empowering the people and democratizing a lot of the tools that have been given to us. So thank you for all of you actually, because it's really you who make this sort of summit worthwhile. Certainly I had a fantastic day. I found it very interesting. So, thank you.